Okay, let's start. Today we have to start the chapter 4, uh, electrical circuits. So chapter 4, we are studying about the more complex circuits and what are the different analysis we have. So in this circuit, what we are studying, you can check. The circuit theorems we will study in this. Not only theorems, we have some more also. So first we will study about the linearity property, how the circuit behaves and which circuits can be used in these theorems. Now, so in these theorems, we have one superposition theorem. We are studying about the source transformation theorem we call, or source transformation also we can say. Next, we will study about the Thevenin's theorem, and last two are Norton's theorem and maximum power transfer theorem. So each theorem has its own advantages and methods of analysis. So all these theorems we have to study. How many theorems we have? One, two, three, four, five major theorems are there, and linearity property is there. So these theorems will be very, very important for your future subjects or future what we call the courses. So today we'll study about the linearity property only because we have some other works. So I will take only 20 to 30 minutes, not more. So just start. So magic circuit secrets. Some secrets what we already studied. We have to recall it. That is, Kirchhoff's law are like magic key for circuits. Why? Kirchhoff's law already we have two Kirchhoff's laws. What are they? Kirchhoff's voltage law, Kirchhoff's current law. So why these are called magic keys? Because by using these laws, it will make understand without changing anything in the circuit. Means if the circuit one is given, means we have some resistances, some sources. If it is given, then without modifying the circuit, we directly get the result of each branch current or node voltages, everything we can get it without any modifying the circuit, without changing the circuit. That's why it is called magic secrets of the laws. That is, Kirchhoff's laws are the magic secrets of the circuits. Now, next we have big circuit mathematics. So, big circuit mathematics, we must go with the like elimination technique, Kramer's rule. This is already what we studied in the previous chapter in mesh analysis, node analysis. That is called big circuit math. Means mathematics included in that. We must know the techniques. Next, circuit gets complicated. So when up to small circuits, okay. When these get complicated is think of circuits like puzzles that got more complex over time because we use them in many ways. I shown in the chapter one a big circuit of the radio, very very big circuit. Many resistances are there, capacitance are there, inductance are there, and amplifiers are there. So if those big circuits when come into picture, these laws cannot work alone. Means the Kirchhoff's law, Ohm's law will not work, not sufficient to finish the job. So for that we have to think more. What is engineering shortcuts we need or special tricks we need to solve those big and complex circuits. So smart engineers made special tricks like Thevenin's and Norton's superposition theorem, source transformation theorem like this. They made a special tricks to make circuit problem easier, to solve the problems very easier. They developed a different type of tricks that is called Thevenin's, Norton's superposition and maximum power transfer, and we have a source transformation theorem. So circuit rules. Now we want to know what is the Thevenin's, what is Norton's, how to use that one. Then we have to follow some rules. So before using those tricks, what are the tricks? These theorems. So before using those tricks, let's learn some basic rules like circuit linearity. Every circuit cannot be used by the tricks. Means there must have some rules. Then we have to check its linearity. If it is linear circuit, homogeneous and additive, then only we can use these theorems. So more tricks. We will also discover the tricks like superposition, source transformation, maximum power transfer theorem. So many tricks are there. So what are the problems? Real world skills. We will use all these knowledge to model sources and measure resistance in real life circuit. It's becoming a circuit expert. When you understand these circuit theorems, then you understand the Ohm's law. When you understand the Kirchhoff's laws, then you will become an expert in electrical circuits. Otherwise, half knowledge. Only I know Kirchhoff's voltage laws, Kirchhoff's current law, and Ohm's law. Enough? No, that's not enough to practice your electrical circuits. So these are minimum things. Up to here only our DC electrical circuits will finish. Then we'll go for the AC. Okay, now start the first topic, linearity property or linear property we can say. So what is linearity property? Linearity is a property of an element describing a linear relationship between cause and effect. Cause and effect means the work and the result we can say. Cause and effect. Element. What is element? Element may be a resistance, element may be a capacitance, element may be a inductance, or element may be a source, voltage source, current source. In this again, dependent voltage source, independent voltage source. Okay, dependent. How many sources are there? Four dependent sources are there. Independent sources how many? Two. One is current source, one is voltage source. Dependent sources, four are there. They are current controlled current source, current controlled voltage controlled voltage source, current controlled voltage source. These are four sources we already studied in the chapter 2. Okay, so we have to think about these elements linearity. Means if we give something to these elements, what the effect? If we give some x value to the element, x difference is coming in the output or not. That's the linear. So in linearity, two properties you have to check. The property is combination of both homogeneity, that is called scaling property, and the additive property. So these two properties you have to check if it is linear or not. If it is linear, by checking these two properties, then we can use any type of theorems. We can use Kirchhoff's law. We can use Ohm's law. Okay. So what is the homogeneity and what is additive we'll study. So what is homogeneity? Homogeneity property requires that if the input is multiplied by a constant, then the output is multiplied by the same constant. For example, let us take, if we are giving some x value to the x multiplication to some factor, then its result in the output should be the same factor. For example, another example, Ohm's law. What is Ohm's law? V is equal to IR. Voltage is equal to current, current and Zerf R, right? Now, if I multiply this voltage with some factor X, then this IR must give the result X only, factor X. That's the linear. Check here. For a resistor R, if you have a resistor R, Ohm's law relates the input I, the output V. So V is equal to IR. So for this is a particular resistor which is a fixed one. Now, for this resistor, if it is a fixed one, when it is a fixed one, if I change the voltage with a X multiplication, then the I must be increased with the X times. I am increasing V with X times multiplication there. Then I must be increased with the X time. Then if the result is coming same, then it is called linear or homogeneity, you can say. First part of the linear. So if the current is increased, the current I is increased by constant K, let us say, constant K I am using here. Then the voltage increases corresponding by the K, that is KIR is equal to KV. Means both sides same multiplication should be there. Both sides same output should come. If voltage is increased by K times, the current should be increased by K times. It's called proportional or linear, we can say. So when it is okay, this is generally Ohm's law. Ohm's law is linear always. Next, additive property. What is additive property? Requires that the response to sum of inputs is the sum of the responses to each input applied separately. Now I have two voltages in two resistances. That is R1, R2 are the resistance. What is the voltage drop in it? It is nothing but IR1, IR2 if they are in series. If they are in series, connected in Java together series, then the voltage drops in these two resistances is nothing but current is same I. So IR1 is one voltage, then the second resistance IR2 is a second. Now if you add these two, how can I write IR1 plus IR2? Now I can take out I common in this. So what happens? R1 plus R2 times I. So I can use combined factor IR1 and IR2, or I can use R1 plus R2 times I. This is called additive. Means Jama together is okay. Is giving the same result. If you separately multiply and Jama also same. IR1 plus IR2. giving the Wahid result. Same it will give I times R1 plus R2. Same result will give. So additiveness is called. Let's see here. Using the voltage current relationship of a resistor, if V1 is equal to IR1 and V2 is equal to IR2, then applying I1 plus I2 will give V is equal to total voltage is equal to I1 plus I2 R I1 R1 I1 R I2 R. Then V1 V2 we can join together. V1 plus V2 can join together. This is called additive. This I1 plus I2 is called additive nature. So if these two factors are okay, we say the resistor is linear element. The resistor we are talking about here resistor only. Resistor linear element because the voltage current relationship satisfy both homogeneity, that is called this one, and additive property, this one. So both are, when I am using resistor with a voltage and current source in a circuit, then it is a linear. We proved here. Okay. Okay. In general, a circuit is linear if both additive and homogeneous. If these two properties start satisfying, then it is a linear. So now I can go further by using different theorems, because this circuit which is having resistance and sources can be is a linear. Okay, a linear circuit consists of only linear elements, linear dependent sources and independent sources. What I told you means the linear circuit must be a linear element. What are the linear element? As per the above example, resistance is the linear element, and it can be a linear dependent source or it can be a linear independent source. Means voltage source, current source can be used here. Okay, coming to the first linearity property. Sorry, example. Okay, linearity property. Example you will have. How it will be. Check. Okay. For this given circuit 4.2, find I0 when Vs, source voltage is 12 and source voltage Vs is 24. Means we are checking the linearity. What is the linearity? First one, property, homogeneity. What is homogeneity? If you increase the input with some factor X or K, the output should be same factor. So that one we will check. So where is the circuit? This is the circuit what we have. Okay, now we have two, 1, 2, 3, 4, 5 resistances we have, right? Then we have one voltage source, Vs, one dependent voltage source. What is the voltage source name of this one? When it is a triangle, it is a dependent voltage source. And which type of dependent voltage source? Based upon here, Vx, means it is depending on other voltage source. So this voltage source is nothing but voltage controlled voltage source. We have four types of dependent sources, right? Dependent sources. Voltage control voltage source, voltage control current source, current control current source, current control voltage control current source. Four we have. So here, based upon the shape, diamond shape, plus minus is given. So it is a voltage source. And based upon the value, means the amount where it is depending, that is Vx, voltage, Vx here. Here it is depending, means voltage. So it is a voltage controlled voltage source. So now what to do? So we have to first identify loops, because here two loops are there, right? So one clockwise I1 and another clockwise I2. Write the loop equation. First loop equation. What we will write in the loop equation here? 6 I1, 2 I1, 4 I1, all are plus, and current entering this one. So it will be entering is plus Vs. Now I2 also there. So 4 minus 4 I2, or another technique I will tell today. So when you are writing the KVL in the loop, what we can do is just sum up all the resistances, then multiply with I1. What is the resistance? 6, 2 and 4. So 6 plus 4, 10 and 2, 12 I1, because all same current is flowing in these three resistances. In these three resistances, same current flowing. So just sum up. 6 plus 2 plus 4, 8 plus 4, 12. 12 I1. And in 4 ohms, another current also flowing, which is opposite direction. That is I2. So put separately. So here this is 12 I1 minus 4 I2, then Bhagi then voltage source. That is current entering here. Entering means plus Vs. We can write like this: 12I1 minus 4I2 plus Vs. This is the first equation. Now second loop, same second loop. How many resistance flowing with I2 currents? Same I2 currents flowing 4, 8 and 4. These three resistors are flowing with the I2 current. So sum of this 8 plus 4, 12 plus 4, 16. So 16 I2, okay, 16 I2, and this 4 ohm resistance also having another current I1, that is opposite direction. So minus 4 I1. So it is minus 4 I1 plus 16 I2 and bagi itne, this one and this one. So when current is flowing out here, coming out, that is from the plus terminal is coming out, means minus 3Vx. It is minus 3Vx. Now here also current is coming out from the plus terminal. This I2 is coming out from the plus terminal. So it is also minus Vs. So these are the two KVL, Kirchhoff's voltage law equations for these two loops. Okay, any doubts in it? Because this you have to practice. Because in the exams, minimum if you write the loop equations correctly, I may give some marks. How to write the equations, you have to practice. Later result is not correct, your method is not correct, no problem. Some marks you will get. Something you will write and give the marks means no, it's not the correct one. Steps should be correct. I will give the marks for the steps. But you must know how to write the loop equation and correct loop equation. How to write the node equation, correct node equations you have to write. Then only I will give marks to the steps. So two techniques I told you. First technique, if you want, I can use the first technique here. First technique is writing the loop equation directly. That is 6 I1, then plus 2 I1 plus 4 I1 minus I2. This is one. Next, what is we have? Entering plus Vs equal to 0. Now rearrange this one. I1 here I1 6 7 8 plus 8 plus 4 12 I1. So 12 I1 minus I2 minus 4 I2, it is there, plus Vs, it is coming. So this is a basic principle, basic method. Another fast method, this one, directly sum up all the resistances for 6 2 and 4 where the same current is flowing I1, that is 6 plus 2 plus 4 12. I1 9, any resistance having the multiple currents, not one current, 4 ohms. This is having I1 and I2 both. And which direction? 4 ohms having this I2 in opposite direction to the I1. So this is minus 4 I2, minus 4 I2. Next, remaining item is Vs. Vs current is entering I1, so it is plus Vs. So like this, we have to have two methods. Okay, which one you practice up to you. In this method, make more equations. In this method, less equations. Second method. Okay. Okay. Now, but Vx is equal to 2I. See here. What is Vx here? This is the resistance and this is the Vx already given Vx. Now what is the Vx equal to? Current is flowing in 2 ohms resistance is I1 and current entering in the plus. So it is 2 I1. Current enters plus means plus it will take. So 2 I1 is the Vx. Now substitute in terms of Vx in the second equation. So it will be 3 into 2 I1, 6 I1, 6 I1 minus 6 I1 minus 4 I1. How much? 10 I1 minus 10 I1. Now remaining 16 I2 minus Vs as it is, then equal to 0. So like this, we just rearrange the equation by substituting Vx is equal to 2I. Now next, now adding these two equations. Now this one, equation 1 and equation 3, we add it. Just add 12 I1 to minus 10 I1. How much? 12 I1 to then it will become 2 I1. Now add minus 4 I2 to plus 16 I2 minus 16 minus 4 12 I2. Now add plus Vs minus Vs, cancel out 0. So it will be equal to 0. Now what is now 2 I1 is equal to 12 I2. 2 I1 is equal to now 12 I2. Now cancel it. 2 means I1 is equal to minus 6 I2. We have to take this 12 I2 that side. Then 2 and 12 cancel. That is divide. I1 is nothing but minus 6 I2 you will get. So minus 6 I2, you got the relationship. Now what we have to do? Next step, substituting in this equation, the above any one of the equation, first or third, up to you. Substitute in first equation, what is I1? Minus 6I2, I am substituting here. So it is 12 into 6. How much? 76. So minus 76 I2 plus there is a 4I2. What is I2? If we substitute, what you are getting here? I will write here. So here, when you substitute here, 12 into minus 6 I2 minus 4I2 plus Vs equal to 0. Now this will give 12 into 6. How much? 72, right? 72, that is minus I2 minus 4I2, right? Yeah, 4I2 plus Vs equal to 0. So minus 72 minus 4, how much? 76. Okay, so minus 76 plus Vs is equal to 0. Now, what is I2? I2 we got Vs by 76. Now we apply the source voltage. How much? 12 volts, and apply the source voltage 24 volts. Two cases. First case, Vs is equal to 12. That is, substitute here. Where? Here in the Vs. Substitute Vs. That is I0. We need I0, right? We need I0. What is I0 here? I0 is nothing but I2. So we need I2 only. I0. We want I0 actually as per the question, which is nothing but I2. So I0 is nothing but I2, which is nothing but what we found, Vs by 76. So what is Vs now? 12. 12 by 76. Then 12 by 76 is the amperes, first case. Now second case, when Vs is equal to 24. So I0 is equal to I2, which is nothing but Vs by 76. Now what is Vs now? 24. So 24 divided by 76. Now check here. First Vs is 12 volts. Now Vs is now how much is increased? 2 times. Now here, when Vs is 12 volts, 12 by 76 is the I2. That is I0. Now when it is 24 volts, I0 is nothing but 24 by 76. How much times it is increasing here? 2 times. Means here when the voltage is increased 2 times, the current also increasing 2 times. So which linearity it is? Homogeneity. Homogeneity means what? Scaling. Okay, multiply with on left hand side, the same result should come on right hand side. Input, if we are multiply, output should get same multiplication. That is homogeneity. So this is called linearity property. So like this, we proved that this is a circuit is linear when it has a voltage source, when it has a dependent voltage source, and when it has a resistances. So we can go further for all the theorems. What are the theorems I told you? Superposition theorem we have, and source transformation theorem. We have Thevenin's theorem. We have Norton's theorem. Last, maximum power transfer theorem. So we have 5 theorems we have to study now. Okay. So here I will stop. So in next class we'll start with the superposition theorem, inshallah. Okay, let's start. I know this is recording, and later also you can study this or listen the video. So now today the chapter 4, the second topic, superposition theorem. First we studied about linearity principles. So now we'll go for the superposition theorem. So what is superposition theorem? Superimposing. Superposition means superimposing, means imposing, and same circuit we are imposing many times. So that's called superposition. So we'll see the definition. The superposition principle states that the voltage across or current through an element in a linear circuit is algebraic sum of the voltages across or currents through that element due to each independent source acting alone. So the statement will not give direct understanding. First, I will give with an example. Let's take I have a electrical circuit with many voltage sources. Let us take I have 3 voltage sources in a circuit. So analyzing with mesh and nodal analysis will give some many steps and more what we call complex equations. Then we got a new technique called superposition. In that, if we have a many voltage sources, for example, current sources again later. First, if we have many voltage sources in the given circuit, then one voltage source will be taken at a time. Remaining all voltage sources, we will neglect it. We will remove it. Then we'll analyze for that voltage source what is the current and voltages in each branch. Then second step, again remove this first voltage source and start with the second voltage source in that circuit and remove all other voltage sources and calculate the all the required values for the branch currents, branch voltages. Then like this third voltage source, like this fourth voltage source. How many voltage source you have? That many times we have to analyze the circuit, each at a time acting with one source only. The same will be for current also. If you have many current sources, then at a time you have to use only one current source and remaining should be open circuited. What is open and short we'll study later. So we have to remove, I can say, remove the remaining current sources and keep at a time only one current source and analyze the circuit to get the voltage and currents in each branch. So later, then again second current source, first current source and remaining current sources, remove it. Act with a only one current source and check the values for the uh, currents and voltages in the branches. So like this, the remaining current sources. This is only voltage source and this is only current source. Now let us take mixed are there. Same principle. If we have some voltage source, some current sources, then we have to remove or remaining all the voltage and current sources, but at a time use only one source. Maybe current or maybe voltage. At a time use one source and start the analyzing the circuit. Then next step, analyze for second source. Third step, analyze for the third source. Like this, if it is finished all the sources, then stop analyzing. Now add all together the values of the each branch voltage or current or whatever required as per the question. Then add together. That is superimposition, means adding together after analyzing individual. Individually we are analyzing and we are adding together. Super joining, we can say superimposing. So that's why the statement states that the superposition principle states that the voltage across an element in a linear circuit is algebraic sum of voltage across that element due to each independent source. Means due to each independent source, means one at a time you have to analyze, then add together all. That is one. Or the superposition principle states that current in that element in a linear circuit is algebraic sum of the currents through that element due to each independent source acting alone. Same thing, this one. So how if we have a one practice problem, then only you can understand easily. So to apply the superposition principle, you must keep two things in mind. First one, we consider one independent source at a time. I told you, if many sources are there, we have to consider only one source at a time, while all other independent sources are turned off. Turned off means removed also, you can say. Turned off means making it zero. Its value make it nullified. It's zero. So this implies that we replace every voltage source by zero, a short circuit. Voltage source, when how it becomes zero? When it become a short circuit. Remove the voltage source and keep as a short circuit, means keep a silk there, short circuit. And every current source zero. Current, how it will be 0 amperes? If you make like a voltage source short circuit, the current become infinite. So for the current source, what we have to do? Remove and make it open circuit. No connection in between those current source. So open circuit the current source. This way we obtain simpler and more manageable circuit. This always why we are going for the theorems, means when there are big and complex circuit, we are going for the theorems. So by using this technique superposition, by using a single at a time source, we make a simpler and manageable circuit by removing other voltage sources by short circuit, removing other current sources by open circuit. What is open and short, we'll see. Okay, what is open? Short circuit. Here previously there was a voltage source. I removed it and I put a silk here, means I put a wire here, short wire. What happens when I put a wire here? The resistance will be zero because the wire minimum or minute value will be there. R can be zero, we can consider. Then voltage also be zero. When R is equal to zero, voltage will be zero because whatever current multiplied by R is equal to zero. What is the voltage? Zero. IR, Ohm's law. V is equal to IR. I put R as a 0 by putting a short circuit, the current. So putting a short circuit, the wire. Then I multiplied by R, whatever with the current, but multiply with the R, what happened? The voltage, it is 0. So it is called short circuit. Now, voltage becoming 0 is by making the circuit short there, means by connecting a silk. Now, what is open circuit? Now, open circuit means current source should be 0. Short circuit means voltage source should be 0. Now, current has to be 0. I want to remove the current. The source current I have to remove. How? When it become I is equal to 0, then it is called a open circuit. How? When I remove the connection here, nothing is connected. Air, open air. Then what happens? There is no connection in between. Then resistance value will be infinite. High, very high value, infinite resistance. When infinite resistance is there, what is the current in the element? V taqsim R, Ohm's law. V is equal to IR. What is I? V taqsim R. So V something divided by R. R is infinite. Something divided by infinite. What is the value? 0. So the current now is becoming 0. So that's why open circuit means I making 0. Short circuit means voltage making 0. How it will happen? In short circuit, connect a silk in between where R is equal to 0, then voltage will be 0. In open circuit, make the open circuit, then R is infinite and current will be 0 by V divided by R is something divided by infinite become 0. So like this is open circuit, and open circuit used for what? For what? Current source. Short circuit used for what? Voltage source in superposition. In superposition, if you want to make voltage source off, means make it short circuit. In superposition, if you want to make current source off, means open the terminal. Remove that and open the terminal. R must be infinite. Okay, second point. 2 points. First point is over. Second point, dependent sources. Now we know that we doesn't have in the universe that only voltage source, only current source we have. We have another type of source. What is that? Dependent sources we have. How many dependent sources we have? 4 types. Voltage control, voltage source, voltage control, current source. Current control, voltage source, current control, current source. Four dependent sources we have from chapter 1 I am telling. So these dependent sources should not be touched. I know that if any voltage source is there, we have to short circuit, make it 0, V is equal to 0. If any current source is there, open it and make it current is equal to 0. Other than 1. 1 should be kept, remaining all should be off. But dependent is there? No, we cannot do anything because it is controlled by other elements. It is controlled by other circuit variables. So that's why we should not do anything with the dependent sources. Only we have to think about the pure voltage source and pure current source, or independent voltage source or independent current source. So this is the definition of the superposition. Now, steps and principle again. Turn off all independent sources except one. So I told you, as per the definition, except one, turn off all the independent sources. Find out the voltage or current due to the active source using the techniques covered in chapter 2 and 3. That is Ohm's law, node analysis, or mesh analysis. So now there is no other sources. Only one source is there. Now it is very easy now to analyze the circuit by using Ohm's law, by using node analysis or mesh analysis. Also other technique also there. What is the other technique? By decreasing the resistance, only making one resistance and finding the current and divide in the other branches. So that also is possible here. So turn off all independent sources except one source. Find output voltage or current due to that active source. Due to that active source, find voltage and current by techniques Ohm's law, node analysis, and mesh analysis. Now think, repeat step 1. The same step repeat for each other independent sources. So step 1 is repeated many times till number of sources is finished, independent sources is finished. If you have 3 independent sources, 3 times step 1 has to be considered. So means followed. Means keep step 1 means keep one source, remaining 2 should be off. Find the voltage currents in all the elements. Second, take the second source, 1 and 3 source should be off, and find the current and voltages in all the elements. Third step, again 1 and 2 source should be off and 3 should be active. Then find all the currents and voltages in all the branches. Now, last step. What is the last step? Find the total contribution by adding algebraically. First step with our voltage source, our source. Second step with Thani voltage source, Thani source. Third step with third source. So with these three different values, we got it. Now add together algebraically. Algebraically means maybe plus or minus whatever the result came. So that you have to add, and that will give the exact result by considering all those examples in three sources were there. So like this, we find individually. I know steps are more, but complexity is very, very low now because only one source is acting at a time. Previously, let's example, three sources are there. Three sources, maybe that may be super node, that may be super mesh, maybe possible is there if three sources are there. So that complexity we are removing by considering only one at a time. Then we have to find three times with the three sources. Now, example, use superposition theorem to find voltage in the circuit, where in the 4 amps, 4 ohms resistance, we need the voltage by having these two sources. One source is 6 volts, one source is 3 amperes. So, 6 volts source is a voltage source. 3 ampere source is a current source, right? Now, are these two are dependent sources or independent sources? Anyone? Are these two are independent or dependent? Dependent sources are signed or identified by using a diamond shape. Diamond shape. Here there is a, what is the shape? Circle. Here circle. So it is a independent thing. If it is a diamond shape, then it is a dependent source. Okay, now first step, what we have to do? We have to consider only one source. That is, I will consider this voltage source and I will remove this current source. Means I can open circuit. Current source removing means I have to open circuit. Just remove the connection from here and here. So the circuit is very simple. 8 ohms and 4 ohms will be, and this is the voltage. So just divide 8 plus 4, 12. 6 divided by 12. How much? 6 divided by 12. Current will be 0.5. Now current is 0.5 is flowing through 8 ampere and 4 volts, 4 ohms. So what is the voltage here? 4 into 0.5, 2 volts is the voltage. Now if you consider only current source, what happens? This voltage source should be short circuit. That is, it should be short circuit here. Means only 8 and 4 will be in parallel with 3 amperes. So 3 amperes should be divided in these two resistances. How it will be divided? Current division rule. What is the current division rule? The other resistance divided by total resistance into total current. So other resistance is nothing but 8 divided by 12. 8 divided by 12 multiplied by 3. You will get some 8 multiplied. Okay, okay, 2 amperes. So 2 into 4, 8 volts will be the second. Now together it will be previously 2 and here 2, 4 volts. We'll check. So first step, what we observe with the superposition, because we have two sources, we will consider this V as V1 plus V2. We consider V as V1 plus V2. Now, V1 will act as a when 6 volt is there. V2 will act as a when 3 ampere current only is there. Now, so V1, how to find V1? By considering only one voltage source, and I will make it as a V1. Previously it was V. Now I am considering only 6 volts. I am not considering this current. So open circuit. So here it is open circuit, no current source here. So I will make it as a V1 and I have to analyze the circuit by loop. By acting, we have many techniques, Ohm's law, and you can use the what we call circuit elimination techniques also you can use, or loop analysis also you can use, mesh analysis. So by mesh analysis, write the equation, current leaving with 6 volts, minus 6. And what is the resistance? 8 plus 4, 12, plus 12 I1, which is equal to 0. So 12 I1 minus 6 volts equal to 0. So what is I1? 0.5 ampere. Just divide it, 0.5 ampere is I1. So what is V1? The I1 is flowing through this 4 ohms. What is V1? 4 into 0.5, it is 2 volts. V1 is equal to 4 into I1, 2 volts. Now, we may also use another technique, voltage division techniques, by finding the V1. Not, you don't want mesh analysis, I want voltage division technique, because it's a very simple circuit. So what is the voltage division technique? It is total, in which branch we want that resistance divided by the total resistance, multiplied the voltage. That is 4 divided by 8 plus 4, 12 multiplied by 6. 4 divided by 8 plus 4 multiplied by 6. This is called voltage division technique. So it's also will give same one. That is 12. So next going to the step 2, V2. When you consider V2, it will be remove this voltage source from here and make it short. Only keep the 3 amperes current. 3 amperes current keep, and this V will become now V2. This V will become now V2. Find V2 now. How to find V2? Some current division rule. That is, to get V2, we set voltage source to 0 in figure this one B. Now using the current division. Current division is other resistance 8 ohms divided by total resistance multiplied by 3. That is total current is equal to 2 amperes. So again 2 amperes into multiplied by 4, 8 volts. So V2 is nothing but 4 into I3, that is 8 volts. Now what is total voltage in this V? What is V is nothing but already we know that V is nothing but V1 plus V2. So V1 plus V2 is 2 already we got, that is V1 2 volts. V2 we got 8 volts, so 8 plus 2 it is 10 volts. So this is your how we will make it simpler method or simpler techniques to analyze this circuit when it has more sources, more independent sources. So we have to take some more bigger circuit. Now let's take another example with bigger circuit with dependent source. Let us take in that. So find I0 in the circuit using superposition. Sorry. Okay. So in this, what we have to find I0. Where is I0? Here. Here I0. In this 5 ohms resistance, I want I0 when there are two independent sources, one dependent source. Okay. So what is our major technique? 2 steps technique we have. First step, okay, I will tell again. Second step was there, when dependent sources like this diamond shape, dependent sources are there, do not touch. Keep it like that only.
Dependence means that.
Dia. Independent means dia. Okay. Dependent means diamond shape. Okay. In that 4 are there. 4 different are there. Okay. Diamond means dependent. Don't worry. Now here dependent, how we know which type of in the 4? This is a plus minus means a voltage source. If it is a direction, it is a current source. But we decide with the another parameter. What is that? What is it is depending? I0 means it is a voltage source basically, but it is depending on current. So it is a voltage current controlled voltage source because I0 is the depending. From here it is depending. So current controlled means current is controlling this. What is this? This is a voltage source. So current controlled voltage source is one. So now there is a two independent sources. One is voltage source, one is current source. So how many steps we can have here? How many circuit analysis we can have here? 2, because we have 2 independent sources, 1 dependent. Okay, 1 dependent is there, or 2 dependent, or many dependent. We should not touch. Only we have to check how many independent. So 2 independent are there. We have to follow 2 independent sources. Means 2 times we have to do the circuit analysis by acting 1 source at a time. So first we can take, okay, I0 we want. As per the question, we want I0. So I0, how can we get first circuit with I0 dash? Second circuit, I0 double dash. What is the first circuit? We'll see. By either this one has to be considered or voltage source has to be considered. We'll check it. I0 dash. Now let us take I0 dash. What I am considering? Okay, I am considering this current source only. So what the voltage source should be? Voltage should be 0. How the voltage source will be 0? By making it short circuit. By making it the connection means 0 resistance value here. So this is the I0 dash. So I0 dash we have to find in the 5 ohms resistance I0 dash. Now assign some currents. Here I will assign currents. It is coming from here to here. That is I3. Then I will assign current. It is because 4 ampere is there. I1. Now we have to write the loop equations. How many are there? 1, 2, 3 loops are there. 3 loops equations we have to write. Now in this I1 loop, as per your super which one? Current super node, as per your super mesh, sorry, as per your super mesh, what is the current is source is not in between two loops. It is independent loop. The current source is independent, not in the in between loop. So the current what we are assumed I1 should be equal to the source current. This is a super mesh what we studied in the previous class, in the previous chapter. I1 is nothing but 4 amperes because it's not shared with anywhere. So it is I1 is equal to 4, directly we can write. So I1 is equal to 4 amperes. Now write the another loop equation for I2. Now I told you the technique for writing the I2. No need to write 1, 2, 3, 4 times the current multiplied resistance. Just check I2, which I am considering how many resistances it is flowing. I2 is flowing in how many resistances? 3, 2 and 1. So totally 3 plus 2. How much? 5. 5 plus 1. How much? 6. So the 6 ohm resistance is having I2. So plus 6 I2. 9. This 3 ohm resistance is having not only I2 but I1 also it is flowing. So separate it. So and which direction with the I2? It is opposite direction with the I2, right? Yes. So minus 3 I1. So this is minus 3 I1. Now further, another step, I1, this 1 ohm. 1 ohm is also flowing I3, not only I2. So this also we have to write. So this current is flowing opposite to this I2. So I3, 1 times I3 is I3. Now last step, this one, this dependent voltage source. How the current is flowing through this, with this loop. I2 is leaving the plus terminal. When current is leaving the plus terminal, what should we consider in the loop analysis? Minus. When entering the plus terminal, it is plus. So it is minus 5I0. So write the loop equation. That is I1 is flowing in 3 ohms. So minus 3I1. Why? Because I1 is opposite to the I2. Next, I2 is flowing all these three resistances. So it is plus 6I2. Now I3 is opposite to this I2. So in the 1 ohm. So minus I3. And current is I2 is leaving from 5I0 dash. So it is minus 5I0 dash. So just remember this equation, correct equation. Just practice how to write the equations. This will give the marks every time I am telling. Now same equation I will write there. First equation already, two equations already we know. That is first loop I1 is equal to 4. We already know, that is with the previous slide. And the second loop already we got minus 3I1 plus 6I2 minus I3 minus 5I0 dash. So like this we have second equation. Now coming to the third loop. Third loop also same like I2 second loop. Third loop I1 is flowing here. Yeah, I1 is flowing in 5 amperes, 5 ohms. I1 is flowing. So how it is? It is opposite to the I3. So minus 5 I1. Now I2 is flowing in only 1 ohm. So it is also opposite to I3. Minus 1 I2. Then I3 plus it should be, because we consider a loop, clockwise loop. So I3 is flowing in 5 ohms, 1 ohm and 4 ohms. Jama all. 5 plus 1 plus 4. How much? 5 plus 4 plus 5 for 9 and plus 1, 10. 10 into I3 plus 10 I3 is the step. Last step, this one also. This is the voltage source. How much voltage? Current entering now. This I3 is entering this plus terminal. So plus 5I0 dash is equal to 0. This is your equation. That is minus 5I1 due to I1, 5. Opposite to I3, minus 5I1. I2, that is I2 is in 1 ohm. So opposite to I3, minus I2. Now I3 is flowing in these three resistances, 5 plus 4 plus 1, 10 ohms, plus 10 I3. Next, plus 5 I0 dash, because current entering the dependent voltage source. Okay, so like this we got three equations. Okay, now substitute I1 is equal to 4 in these equations, we can simplify. Still, we have how many unknowns? I2, I3, I0 dash. We have two equations, three unknowns. Can we solve it? No. So for that we need to, let me check. So now, but at node is equal to 0, because we have a super node here, node here. So we need to have a node equation also. KVL and KCL also we need. Super mesh we have. Already KVL is done. We need KCL also at this super node. That is this 0 node. 0 node, what are the current directions? I1, I0 is I3 and I0 dash is entering. I1 is leaving. So I1 is equal to I3 plus I0 dash. So I3 will be I1 minus I0 dash. So already we know what is I1. What is I1? 4 amperes. So I3 is already we know 4 minus I0 dash. Now we got 1 sorry, 1, 2, 3, 4 equations. And how many unknowns? 4 unknowns. I1, I2, I3, I0 dash. 4 equations, 4 unknowns. Can we solve the equation? Can we solve the parameters? Yes, easily we can solve the parameters by you can use the elimination technique also you can use, okay, or you can use directly the calculator, no problem. So substituting in the all the above equations, how can we calculate? Just check what I am doing. Just I am writing here. What is 5I1? What is I1? 4 amperes. So 5 into 4. Sorry, first equation. 3 minus 3I1. 4 into 3 minus 3 into 4. That is due to I1. I2 is as it is 6I2 minus 4. That is I3. What is I3? 4 minus I0 dash. So minus 4 minus or minus plus I0 dash. Next minus 5 I0 dash minus 5 I0 dash. We got one equation called minus 12 by using minus 12 plus 6 I2 and 4 minus 4 and plus 1 minus 5 minus 4 I0 dash. One equation we got. Simplifying these equations. 4. Now simplify this equation. Now simplify again. What happens? Take 12 other side and divide both sides with 2. So, okay, to minus 12, sorry, minus 12, minus 4, how much? Minus 16. Then take other side. It will become 16 this side. Now it will be 6I2 and minus 4I0 dash. Now divide both sides with 2. 6I2 will become 3I2. 4I2 I0 dash will become 2I0 dash. This 12 plus 4, 16 will become 8. So like this is simplified. How many unknowns here? I2 minus I0 dash. 2 unknowns. So we need another equation with the same 2 unknowns, then we can solve this. So now consider this equation. Now when you consider this equation, multiply 5I1. What is I1? 4 amperes. So minus 4 multiply 4 minus I2. Then I3. What is I3? 4 minus I0 dash. I3 is. So it is 4 minus I0 dash. So 10 times 4. That is 10 times 4 minus 10 times I0 dash. So by multiplying with 10 this one. Now plus I0 dash. 5 I0 dash. Now rearrange this. 5 4s are 20. Minus 20 minus I2 and this is 40 plus 40 and minus 10 plus 5. It becomes minus 5 I0 dash. Now simplify this one. Take minus 20 and plus 40. How much? Plus 20. So 20 here only. Now take this I2 other side and I0 dash other side. So I2 plus 5 I0 dash equal to 20. I2 plus 5 I0 dash equal to 20. So by using this equation and this equation, 2 no unknowns and 2 equation, we can solve it. We got I0 dash because we need only I0 here. I0 dash only we need. So I0 dash is 52 by 17. Just keep it aside. First circuit is done. Now come with the other circuit with other source. What is other source now? Voltage source. Current source should be open. That will be simple inshallah. Now the second circuit is considering only this voltage source and the current source is open. Now we have only 2 loops. Easy now. Previously we have 3 loops. Big analysis. No problem. Here now 2 loops. Now find first loop. What is the first loop? I4 and I5 you can say. Okay. 3 and 2 and 1. In all 3 resistances, I4 is flowing. 3 plus 2 plus 1. 3, 4, 5, 6, I4. Minus current is flowing in 1 ohm with I5 current. Minus I5. Now dependent voltage source. Current is leaving from the plus terminal. Which loop it is taking? Loop 4. Yeah. Yeah, current leaving. So minus 5 I0 double dash. Okay. Current leaving. If you current entering, it should be minus. Entering, it should be plus. Current leaving the plus terminal, it should be minus 5 I0 double dash. So this is the loop equation for this loop, 4th loop. Now coming to the 5th loop. 5th loop, 6, already we know what is the 4th loop. Now coming to the 5th loop. 5th loop, current is I4 is flowing in this only this resistance. So opposite to the I5. So minus I4. This is minus I4. Now the I5 is flowing in these 3 resistances. So what is this? 5 plus 1 plus 4, 9 and 10. 10 I5 plus 10 I5. Now what is the this one voltage source? Current leaving is the voltage source. What is this? Minus 20 current leaving. Now current I5 is entering this dependent voltage source. So plus I5 I0 double dash. So we got to simplify this one. We then I substitute. What is I5 is equal to here? What we consider this I5 as? I5 is nothing but I0 double dash minus I0 double dash opposite to this one. So substitute I5 as minus I0 double dash in the previous equation. That is 6I4 minus 4I0 double dash. Same here also. I5 if you substitute, that is 6I4 minus I5, that is nothing but I0 double dash. If you substitute here minus I0 double dash, 5 and 1. Minus or minus, it will be plus. So 5 minus 1, 4. So minus 4 I0 double dash from this equation. Now from this equation, substitute I5 as a minus I0 double dash. So it is minus 10 I0 double dash. So plus 5 I0 double dash. It will become plus 5 I0 double dash. So to take 20 other side, now rearrange this one, it will become I4 plus 5 I0 double dash equal to minus 20. So just substitute this I5 equal to minus I0 in this equation, you will get this one, this equation. So now we got I4 and I0 double dash, I4 and I0 double dash in these two equations, two unknowns, two equations. Solve in any technique, elimination or Cramer's rule, you will get I0 double dash as minus 60 by 17. What is the previous one? I0 single dash. Now the original circuit. Now what is I0 single double dash? This is I0 single dash 52 by 17 by previous slide by considering only this current source. By considering this only current source, we already find I0 single dash is 52 by 17. I0 double dash is considered by this voltage source, and removing this we got minus 60 by 17. Now what is I0? What is I0 here? It is nothing but I0 dash plus I0 double dash, two currents at a time. So join together. So it become minus 8 by 17. 60 minus 52, 8. So minus 8 by 17, which is equal to minus 0.4706. So like this, this is comes in the big answer question. Maybe in final exam for 5 to 6 marks. In the mid exam, 4 to 5 marks. So this have many steps. So that's why practice more like these examples. So like this is a superposition theorem. We'll stop here. Next, we study source transformation in the next class. Okay, let's start. Now, today we have to start the second, third, I think, right? Yeah, linearity we finished in the chapter 4, and we have finished what is superposition we finished. Now, which source transformation we have to finish today. Now, source transformation technique is a very useful technique for making complex circuit into the simple circuit. What is it? A source transformation is a process of replacing a voltage source in series with a resistor by a current source in parallel with a vice versa. Okay, so let's take we have one voltage source in series, one resistance, one combination, two element combination we have. Let us take series. When voltage is there, remember resistance should be in series in a combination, no other elements connected in between. Okay, so then we can convert these two, the voltage source and resistance together, we can convert to a current source with a parallel resistance. Resistance will not change here because it's a physical quantity. It will not change. Only it was in series with the voltage source. Now it will come as a parallel with a current source. So if you see the picture, you will understand, inshallah. So now let us take, this is your voltage source. In series, there is a resistance between terminal A and B. Now, this will satisfy Ohm's law. V is equal to IR. We know it. Vs is the voltage source. Which one? Dependent or independent? Independent voltage source. If it is dependent also, no problem. So it is a independent voltage source and resistance are there in series at a terminal A and B. Then we can directly convert this into a current source and a resistance in parallel with the same terminals A and B. With the same terminals A and B, just I am converting. It's called transformation, means conversion. We cannot say conversion. We are just rearrangement, we can say, by calculating its values and rearranging with a current source and a resistance in parallel. Previously, the resistance was in series with the voltage source. Now, the same resistance, without changing its value, it will come in parallel with the current source. It's called transformation. We are transforming from voltage to current. So this is called source transformation. It is applicable only for the sources, maybe dependent or independent. So the two circuits in the figure are equivalent provided they have same voltage current relationship at terminal A and B. What do you mean this? They must have a same voltage current relationship, means Ohm's law. They must satisfy the Ohm's law principle. The voltage and current relationship means what? V and R, I and R must have the same relationship, means Ohm's law should satisfy there. So if the sources are turned off, means when the sources are turned off, the equivalent resistance at terminal A and B in both circuits is R. Now let us take, if voltage source here is turned off, what do you mean? In superposition we already studied. Turning off of voltage source means what? Means we are making V is equal to 0, means we are making a short circuit here. We are just removing the source voltage and we are short circuiting here. Means there's nothing will be there, but there is a continuous path will be there. So between terminal A and B, when there is no Vs and there is a silk here in between, then it will be R only remain, means only resistance will be there. Same in this circuit also. When you switch off the current source, what do you mean switch off the current source? Means just we have to open circuit. IS should be 0, means it must be open circuit, no connection between from this point to this point. So at that time also between terminal A and B only R remains. So in both cases, when the source thing is off, maybe voltage or current source is off, only resistance will remain between terminal A and B. Terminal A and B only resistance will remain. So that is the second case we are testing. Means this is also satisfying, and voltage current relationship also satisfying. So these two, when it is satisfied, then source transformation is okay. We can do the source transformation. That is, a voltage source in series resistance can be transformed to a current source in parallel with a resistance. Another point, when terminals B are short circuited, when these two terminals are short circuited, what happens? Why a closed loop will come, and the current here, the IS, short circuit current, is nothing but the total voltage Vs divided by R. Total voltage Vs divided by R is nothing but your current ISC in the circuit on the left hand side, this side. And if the same here, if you short circuit, if you want IS, same the current will be multiplied by R is nothing but your voltage at A and B. And on the right hand side also same will current, and this IS is given by this voltage A and B, because in parallel circuit voltage is same. So voltage A and B, VAB divided by R is nothing but your IS, which is equal to ISC, and that is given by Vs by R. So what is here Vs? This one, Vs by R. So thus Vs by R is nothing but the source current. Thus when short circuit here, what is the IS? This IS is nothing but the Vs at the terminal A and B divided by R. So Vs by R is nothing but your IS. So for the two circuits be equivalent. So at the, we can test another thing also. These two are equivalent. 3-point cross check we did it. First cross check, voltage current relationship is same. And the second cross check, and when you short circuit this A and B terminal and when you switch off the sources, then the remaining should be the resistance only, that we tested. The third one, when you short circuit A and B terminal, the current ISC is nothing but your Vs divided by R. Now here also when you short circuit A and B, the IS is nothing but Vs by R. So this is how we just transform the voltage source with series resistance to current source parallel resistance. Okay. So source transformation requires that Vs is equal to Ohm's law, IS is equal to Vs by R. This is you have to remember. Now we have two examples with me. Then we can practice. Now let us take Vs and R same one. Now see, we should keep the following points in mind when dealing with source transformation. What are the 2 points? That the arrow of the current source is directed towards the positive terminal of the voltage source. Now here plus minus is like this. Plus is up and minus is down. Then when you transform it, the current should be upward because plus is on the top. So it's like this. Now if it is, let us take plus minus is reverse. Here plus is down and minus is up. Then current direction should be downward. This you have to keep in mind. Second point, the source transformation is not possible when R is equal to 0. We know that source transformation means a voltage source in a series resistance can be transformed to a current source with a parallel resistance, right? Now, when R is equal to 0, it is not possible to transform to the current source because when R is equal to 0, the voltage source become an ideal voltage source, which is not possible in the universe. Any voltage source will have a leakage resistance. We call that resistance always will there, which will be act as a in series with the voltage source. Same current source is always have a leakage resistance. Then that will be connected across the current source in parallel. So that's why when R is equal to 0, then source transformation not possible from voltage source to current source. When R is equal to infinity also, current source to voltage source also not possible. What is R is equal to infinity? Means a very high value. So current will be 0. So it is not possible. So these 2 points you have to note down. Now take the problem. So use the source transformation to find V0. Where is the V0 here? Use the source transformation to find V0 in the circuit given. So, okay, before, what is the definition of source transformation? Any voltage source in series, a resistance can be converted to a current source in parallel resistance or reverse. Any current source in parallel resistance can be converted to a voltage source in series a resistance. So see here, what possibility we can do? First possibility on the right hand side, a voltage source 12 volts and 3 ohms resistance in series are there. Can I convert this into current source and a parallel resistance? Yes. Why? Because these two are in series and they obey Ohm's law. Nothing is connected in between. So what is the Ohm's law? V is equal to IR. That is 12 is equal to I into R. That is I into 3. So what is I then? I will be V divided by R. 12 divided by 3. How much? 4. So 4 amperes current will be generated or can be transformed to current source. That is from voltage source 12 volts, it can be transformed to as a 4 ampere current source. Now where should the resistance should be placed? In parallel to the current source. First on the right side. Now second on the left side, there is a current source and there is a parallel resistance. Now this is also one combination. We can convert or we can transform into voltage source with a series resistance. So what is the Ohm's law here? V is equal to IR. So multiply 3 amperes and 4 ohms. So how much? 12. 12 volts is the voltage source. In series, a 4 ohms resistance will come. Now these 4 ohms and 2 ohms will be added together. 6 ohms will come. We can see it. Now check here. Check the circuit here. So same circuit I draw. First on the left hand side. From the left hand side, V is equal to IR. This 4 and 3 ampere. V is equal to I is 3 ampere. R is 4. So 12 volts. So here a voltage source will come. 12 volts and in series 4 ohms. Now on the right hand side. From the right hand side, this is the 3 ohms and 12 volts will convert as a current source. That is I is equal to V by R. That is 12 by 4, 4 amperes. So that will act as a 4 amperes and 3 ohms in parallel. Check how the resultant like this. So on the right hand side, this 12 and 3 will become 3 coming in parallel and the voltage source becoming current source by calculation like 4 amperes. Now on the left hand side, this 4 ohms and 3 amperes becoming a voltage source of 12 volts. This 4 ohms will come in the series. Remaining circuit is same. Remaining circuit is same here. 4 and remaining 2 ohms and 8 ohms is same. Now I am not changing that one. Now 4 ohms and 2 ohms now becoming series. So just add it up, 6 ohms. Now when this 6 ohms and 12 ohms are in series, now this voltage source can be transformed to current again. 12 and 6. So what is the current source? 12 divided by 6. 2 amperes. So 2 amperes current source will come, and in parallel 6 ohms will become in parallel. Okay, that's also possible there. From left hand side, the current source 12 volts and total resistance is 6. So the current will be 2 amperes. Now rearrange the circuit. This part, left hand side, this part will become 2 amperes current. Now check here. How is the voltage source? Current is downwards. So voltage also we have to write minus plus. Same current also downwards. Be careful that one. Now this is 6 ohms because 4 plus 2 is 6, and this 12 and 6 ohms, 12 volts and 6 ohms, the current source will be 2 amperes. Now, so 2 amperes and 6 ohms, we got it. Now 8 ohms as it is, we kept, no, because we have to calculate V0 here. Now this also I didn't change. Now observe here, 6 ohms and 3 ohms, these two are in parallel. What will be the result? 6 and 3, 6 into 3 divided by 6 plus 3. So it becomes half. That is 6 into 3 divided by 6 plus 3, 9. 3, 3 is yeah, 2 ohms will come, right? Yes, it will become a 2 ohms. Now current. Now current is downwards and the current is here upwards. Both are parallel. When parallel currents are there, there should be a minus. So 4 minus 2, it will be 2 amperes current will come. Check here. 6 and 3 are in parallel. These resistances are in parallel. So 2 ohms will come. Now 2 amperes and 4 amperes are in parallel. So it becomes 2 amperes because 2 into 4 divided by 6. So it will become 2. So now rearrange this circuit. So 6 and 3 is becoming 2 ohms here. Now 4 and 2 amperes current becoming 2 amperes. So we have the final circuit here. Now what we need? V0 we need. Now for that also again we can transform. What we can transform? 2 ohms and 2 amperes are in parallel. So we can transform into voltage source. What is the voltage source equation? V is equal to IR. 2 into 2. How much? 4. 4 volts is the voltage source. We can transform it. Okay. That also we can transform. This is the one way. Another way, directly current division rule also we can do. Two methods I am telling. Second method is there here. That is using current division. What is the current division? I want current in 8 ohms. So what is the rule? The other resistance 2 ohms divided by total resistance multiplied by the current. So other resistance is the 2 ohms divided by the total resistance 2 plus 8 multiplied by the total current. So then you will get the 0.4 amperes. So once you get the 0.4 amperes, what is the V0? 8 into I, 2.4 volts. So V0 is, 3.2 volts. Now another method also we have. Alternatively, since 8 ohms and 2 ohms resistors are in parallel, 8 and 2 are in parallel. Okay. And V0 across them. So both are V0 across there. Then hence what we can write? V0 is equal to 8 into 2 parallel. What is 8 into 2 parallel? We will get 8 into 2 divided by 10 multiplied by 2 amperes. So it will get to 3.2 same. Two methods, two techniques. Another technique also I have. Here it is not mentioned. What is that? Convert this current source to voltage source. That is 2 into 2, 4 volts. And in series 2 ohms. So 4 volts in series 2 ohms. So total resistance will become 8 plus 2, 10. So 10 ohms. 4 divided by 10 ohms. So 0.4 is the current, right? Same 0.4. Now multiply 0.4 with the 8, it will get 3.2 volts. So 3 methods is possible here. So like this, we can transform the sources from voltage to current and current to voltage. Then we can minimize the circuit and we can get the result in easy fashion without any big errors. Another example we'll see. Okay, in this example, we have a dependent source. Which dependent source? Can anyone? Which type of source it is? Current or voltage? Arrow is there inside. I know it is a dependent because it's a diamond shape. Inside there is a saham. Arrow is there. So is it a current source or voltage source? It is a current source because arrow is there. If plus minus is there, it is a battery voltage source. When arrow is there, it is a current source. Now, which type of dependent source? It is a current source basically, but it is having a dependent on Vx. It is a depending on Vx. Vx means voltage. So it is a voltage controlled current source, basically current source. Okay, so it is a voltage controlled current source. Now we have to solve the equation, solve this problem by finding Vx. Where is the Vx? Yeah, at 2 ohms we find to find what is the voltage across 2 ohms resistance, that is given as Vx. We have to find this. So how to do that one? Let's see. Sorry. Okay, now okay, yeah. Now let us take these two, 6 volts and 2 ohms. I can convert into current source. Yes. So how we can I is equal to V by R. 6 by 2. That is 3 amperes. I put it 3 amperes up the up direction because plus is up. Now 2 ohms is coming in parallel. Now these 2 ohms I should not touch because it is a Vx we have to find here. Now here again 18 volts. There is no in series resistance, so I cannot change. So 18 volts as it is. I am not changing. Now these two dependent also source transformation possible. I told you. So there is a current source and there is a resistance. So I can convert it into voltage with in series a resistance. So how voltage V is equal to IR. What is I? 0.25 Vx. R is 4. Multiply 4 into 0.25 is 1. So 1 Vx. So 1 Vx. That is Vx is the dependent voltage source. Current direction is on the left side. So plus is on the left. Next, what is the resistance? 4 ohms. It's coming in series with the voltage source. So these parallel become now series with the voltage source. Now this is one step. Second step again. What we can do now? Now we have to, yeah. Second step, yeah. Now these 2 ohms and these 2 ohms, what is happening in parallel? When 2 ohms resistance are in parallel, resultant will be 2 multiplied by 2 divided by 2 plus 2. So becoming half. So 1 ohm. So 1 ohm resistance will come here. So this 1 ohm resistance and 3 amperes current source again converted into voltage. So what is the voltage equation? V is equal to IR. I is 3 amperes. What is the resistance? 1 ohm because of these two parallel. So 3 into 1, 1. So 3 volts. 3 volts. 3 into 1, 3 volts. Now 1 ohm is the resultant resistance. So I am keeping in series. So this is now new circuit. I am not changing here. Now here we need Vx at these 2 points. This point and this point Vx. So I keep that as a plus minus Vx only. So now our next step starts. What is the next step? Same explanation is there, don't worry. Now in this, we have to apply Kirchhoff's voltage law, KVL loop equation for this complete loop. So what happens? Apply the KVL to this complete loop. Start from here. Current I is there. So when current leaves the plus terminal is plus or minus? Minus. Current leaves the plus terminal is minus. So minus 3 volts. Current enters here. So plus I and plus 4i. So total plus 5i will be there. 5i. Now current enters the plus terminal. So it is plus. So plus Vx. Current enters the plus terminal. It is plus 18 is equal to 0. Just check. See, minus 3 because current leaves the plus terminal. 4 plus 1, 5 ohms resistance multiplied by current I, that is 5i. Now plus Vx because current is entering the plus terminal here. So it is Vx. Current is entering in the another source plus terminal, so plus 18. So like this, we got this first equation. We need another 2 equations, then only we can solve. Because to another equation we need, then only we can solve because I is unknown, Vx is unknown. We need another equation with these 2 unknowns. So next here, 2 possibilities are there. Either take this loop equation and this loop equation separately. Up to you, anyone, both I will tell. So now draw this loop equation first. Same I. So it will be minus 3 and plus I and current enters here. So what happens? Plus Vx. We can write that one. Minus 3 plus I plus Vx. Current enters. The first loop equation is here. I am writing this loop equation because we need voltage here Vx. So that's why I write separately this loop equation. So minus 3 plus I plus Vx equal to 0. So I can write Vx is equal to 3 minus I from this equation. 3 is going other side and I also other side. So 3 minus I. Now substitute Vx in this equation. What happens? Check. So 18 minus 3, it is 15. So 15 I kept here. 5I I will kept here. Now what is Vx? Vx I am taking from the above equation 3I. So 3 plus 3 minus I. So 5I minus I, how much? 4I. So 4I take other side. So sorry, 4I. Okay, now 15 plus 3, 18. Take other side, minus 18. Minus 18 divided by 4. It is 4.5. Minus 18 by divided by 4. It is minus 4.5. Current is here 4.5. Now calculate Vx. How to calculate Vx? Okay, another method is apply the loop here. Later we calculate Vx. First check another method. Apply loop here. So current leaving here. So minus Vx, current entering. So 4I, current entering plus Vx, current entering plus 18. So minus Vx plus 4I plus Vx plus 18 is equal to 0. Now here also if you substitute from this equation Vx is equal to 3 minus I, you can get I is equal to minus 4.5. Now we got I. Now what is Vx we need as per the equation? What is Vx? Vx is equal to, already we know, 3 minus I. So 3 minus 4.5. I already we got minus 4.5. So 3 minus of minus 4.5. So 3 plus 4.5 it is. So it will become 7.5. 3 plus 4, 7. 7.5. So like this we have to solve the source transformation technique. This is short answer questions only, don't worry. So next our technique is Thevenin's theorem, Norton's theorem and maximum power. These three is in chapter 4. So today we study about Thevenin's, just basic part, problems we'll do in the next class. So Thevenin's theorem. Thevenin's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of voltage source V Thevenins in series with the R Thevenins. Like your source transformation technique, what we are doing? The source transformation technique from, so if we have current source in parallel with the resistance, we are converting into a voltage source in series resistance. Here also say almost same. We are converting the complete circuit into a voltage source with Thevenins in series a Thevenin's resistance. Means let us take we have 100 resistances, many voltage source, current source, dependent source in one circuit. Now I am just simplifying the circuit and making it as a one voltage source and one resistor. That's it. Means all will be simplified into two parts. That is two elements. One is voltage source, that is called V Thevenins. Another element is resistance, that is called R Thevenins. These two if we keep it, and on the right hand side keep the what required element we want to analyze. Like we want to analyze in another resistance how the behavior will change. So that we can do. So what is, again I will read the definition. Thevenin's theorem states that a linear two-terminal circuit can be replaced. Means a linear two-terminal circuit. In the two-terminal circuit, maybe many resistances मौजूद, maybe many voltage sources, current sources, dependent sources मौजूद, but can be replaced. Means we have to replace it by an equivalent circuit. Means a modified equivalent circuit. Only simple circuit, equivalent circuit consisting of a voltage source and a series resistor. Only two items. Maybe so much big, but it can be replaced with a voltage source and a series resistor that name as V Thevenins and R Thevenins. Where V Thevenins, what is V Thevenins now? Or where V Thevenins is the open circuit voltage at the terminal. Means we considered a two terminals, some big circuit. Now we are making that circuit equivalent. So V Thevenins is nothing but in that open circuit A and B, if you are taking that, by seeing from that side, A and B side, what is the voltage coming at that point? That is equivalent voltage. So that is called V Thevenins. Now, what is R Thevenins? R Thevenins is the input or equivalent resistance at the terminal when independent sources are turned off. Now, resistance, how you calculate the resistance, total resistances? By turning off all the sources. What are the sources? Sources are of two major types: dependent source and independent source. Okay, in this dependent source we have four types. Already we know: voltage control voltage source, voltage control current source, current control voltage source, current control current source. So like this we have four dependent. Another independent, we have two: voltage source and current source. So these six categories, whatever we have to turn off. Turn off technique, I already told you. Turn off technique will work only for what? Independent sources. What are they? Voltage source and current source. These two are the independent. So what are the turn off techniques? For voltage source, we have to short circuit. We are making a silk there. We are making a connection there. Short circuit. Zero resistance, zero voltage. We are connecting a wire there. For a current source, we are open circuiting that one. Infinite resistance means open circuiting that point when current source is there. So these two techniques, by apply to the remaining circuit, apply these two techniques means switch off the voltage and current sources and find equivalent resistance by elimination technique: parallel, series, parallel, maybe star delta, whatever you want, you can use it. Find equivalent resistance with one only, R equivalent. Then that is called R Thevenin's. See here. Now let us take, we have this complete circuit where A and B is a terminal, where on the left hand side the linear two terminal circuit is there. Linear two terminal circuit, big circuit may be available, very big circuit. Now on the right hand side, load resistance, maybe one resistance load, where we want to see the performance when there is a change in the linear circuit. So only one resistance on the right hand side, load resistance we can say. On the left hand side, the complete circuit is there with many sources, many resistances. So this complete big circuit where left hand side on the A and B, we have to convert it with a one voltage source, one resistance. So that is called your Thevenin's theorem. Once you got these two, then we can find easily all the values of change in the current, change in the voltage. The analysis we can do in small time. So what are the steps? According to the Thevenin's theorem, the linear circuit in figure A, this one, replaced by B. So this can be replaced by this. Means this linear circuit can be replaced with a Thevenin's voltage source and a resistance in series. Now the circuit to the left of the terminal is known as the Thevenin's equivalent circuit. Left of the terminal. This is called your Thevenin's equivalent circuit. Next, in figure, the Thevenin equivalent circuit V Thevenin's is the open circuit voltage across. What is the V Thevenin's? Is nothing but just remove this load resistance and open it. Between A and B terminal, whatever the voltage is coming, by solving the circuit, that is your V Thevenin's or open circuit voltage. Both are same. Now, what is the Thevenin's resistance? Thevenin's resistance is the input resistance at terminal when the independent sources are off. I told you here, dependent will not touch, only independent will touch. Independent sources are off. Dependent will be as it is. So, independent sources, voltage source should be short and current source should be open. So, what is the Thevenin's? In this open circuit, A and B terminal open, just remove this load and make independent sources off and find the equivalent resistance. Then it is called R Thevenin's. Now, see here how we are. So what is V Thevenin's? Is nothing but just remove the load resistance and at terminal A and B, what is VOC is coming by solving this complete big circuit or small circuit, that is your V Thevenin's. Now same circuit at the terminal A and B, see from this side on the right side, solve this complete circuit by switching off the independent sources. Voltage source short circuit, current source, voltage source short circuit, current source open circuit. Then you will get some equivalent resistance in between A and B. That is nothing but R input, that is R Thevenin's. So like this you have to calculate. Okay, this slide the later will stop. To find Thevenin's theorem, case 1. What is the case 1? Check here. R in we have to find. Then this is open circuit, V Thevenin, this is R Thevenin. Now R Thevenin, how to find? If the network has no dependent sources, very good. If there is no dependent sources, then we turn off all independent sources. R Thevenin is the input resistance of the network looking between terminal A and B. So looking between terminal A and B, switch off all the sources, then find the equivalent resistance. Case 2, when what happens in the case 2, check. Case 2, to find R-Thevenins, because sometimes there will be a dependent sources also. So that the time big problem. So what we have to do? We have to apply small voltage. If the network has dependent sources, we turn off all independent sources, just switch off all the independent sources like case 1. Now we apply a voltage source V0 at terminal A and B. Some small voltage, 1 volt, 2 volt, whatever you decide. Just apply a V0 voltage and find, okay, apply at A and B and then determine resulting current I0. Then because of this 1 or 2 volts of V0, find the current I0 what is going inside because of this source. Because all other independent sources are off. There is no generating source inside. Only dependent are there. Okay. But what exactly giving is from outside. That is terminal A and B on the right hand side. So whatever the voltage is we are giving, that will give the current. So that current, if you find, is nothing but your R Thevenin's V0 by I0. If you know that current I0, V0 already we know what we gave. So R Thevenin's is nothing but V0 by I0. So like this, we will find. Now another technique. Or you give a current source with current source 1 ampere, 2 ampere. Find the voltage V0 at terminal and A and B. Then what will be the R Thevenin's V0 by I0 again. Alternatively, we may insert a current source I0 at terminal A and B as shown in figure and find terminal voltage V0. Again, R Thevenin is nothing but same V0 by I0. So, in either approach, we may assume any voltage of I0 and V0. Here also, voltage you are applying or current you are applying, you can assume anything 1 volt, 2 volt, or 1 ampere, 2 ampere, up to you. Okay, so like this we have to do. And yeah, as mentioned earlier, a linear circuit with a variable load can be replaced by a Thevenin's equivalent exclusive of the load, means load is removed. The equivalent network behaves same way externally as original circuit. So on the right hand side, we are keeping RL. On the left hand side, a linear circuit that can be converted with a V Thevenin's and R Thevenin's. Okay, now this is equivalent. Again, we are simplifying. Now next, the current IL, okay, the current IL through the load and the voltage VL across. What is the current through the load IL and the voltage VL at the terminal A and B is can be given by VL is equal to IL is equal to total voltage divided by total resistance, that is R Thevenin's plus RL. Same. If you want VL, RL into IL. So R, what is IL? We can write here RL by R Thevenin's plus RL V Thevenin's. So like this, we have to calculate the load current, load voltage. So we have examples. In next class, we'll study that one. Assalamu alaikum. Now, in today's class, Thevenin's theorem and Norton's theorem will cover. Thevenin's theorem, the theory topic, I already finished in last class, so just I will revise in 1 or 2 items. So Thevenin's theorem, as per the definition, let's take, okay, yeah. So a linear circuit with a variable load can be replaced by a Thevenin's equivalent exclusive of the load, means you have to remove the load resistance and it can be replaced with a Thevenin equivalent circuit. The equivalent network that after removing the load, what we are calculating the Thevenin equivalent network behaves the same way externally as the original circuit. So the original circuit may have many sources, many resistances, many elements, and many dependent sources, independent sources, whatever. So it will behave exactly as the original circuit, the Thevenin's equivalent network. The equivalent network will have one Thevenin source and one Thevenin's resistance in series. So the Thevenin source is the voltage source and the resistance will be connected in series. This is the Thevenin's theorem. Now, how to calculate the, I will tell that one again. So this is, let us take A and B is the terminal where our external load resistance is connected, where we have to find the behavior of the network that is a linear circuit. Then what we have to do, we have to just remove this RL resistance where we want the exact what is the current and what is the voltage in this branch. Then an open circuit of A and B, look back to this linear circuit, find the R Thevenin's, that is equivalent resistance of the complete circuit, whatever the big circuit, by removing the voltage source, means short circuiting, and by removing the current source, that is open circuiting the current source. Dependent sources should not be touched. It will be as it is because they are depending on other elements. Then what we have to do, then again short circuit A and B here and find the what is the current, so that we can find the what is the Thevenin's. So just define, consider linear circuit terminated by RL as shown in figure. Next, which can be replaced with a Thevenin's and R Thevenin's. How to do that one? The current IL through the load and the voltage VL. The current through the load IL and the voltage across this RL A and B is obtained from this figure is we can obtain by IL is equal to, what is IL is equal to, there are two resistances, nothing but other resistance, sorry, total voltage divided by the total resistance is nothing but your current IL. Now what is the voltage across RL is nothing but IL into RL. What is IL multiplied by RL? Substitute the IL equation here, that is V Thevenin by R Thevenin plus RL and multiply RL. So generally voltage division rule also we can use here, that is same resistance divided by total resistance multiplied by the total voltage, that is voltage division rule. So like this Thevenin's theorem we have to find. So already I told you how to find the V Thevenin's and R Thevenin's. Now let's have an example here. The example have how many elements? Now check here. One, two, three, four, five elements we have. In that, one is voltage source, one is the current source. These are independent ones, so no need to worry. So just across this element number 6, that is where we want the Thevenin's equivalent resistance and the voltage, Thevenin's voltage. Just remove this RL and calculate the effectiveness. F means R equivalent. So just find the Thevenin's equivalent circuit of the circuit shown in figure to the left of the terminals A and B. A and B on the left side, whatever is the effective original circuit where we need a equivalent circuit with the Thevenin's voltage source and a Thevenin's resistance. Then find the current RL. Then the current the RL resistance. What is the current IL we want? When RL is equal to 6 ohms, 16 ohms, and 36. So RL I am varying. So what is the benefit of Thevenin's now? You can understand here. Means one time RL is 6 ohms I am keeping. I want what is IL. So by conventional old methods, that is Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, and KVL, loop analysis, nodal analysis, we have to find completely all the analysis, that is loop equation, node equations, one time for when R is equal to RL is equal to 6. And second time, same method we have to follow when RL is equal to 16. And third time also we have to follow when RL is 36. Means every time we have to solve the equations, many steps. So what we are proposing here is just you find the what is the equivalence between A and B terminal on the left side with one voltage source and one resistance. Then every time only we have to change with one equation what is IL. IL when R is equal to RL is equal to 6, IL when RL is equal to 16, IL when RL is equal to 36. That's it. So find that in three steps you can find. So in first time only we have to find equivalent resistance, that you have the steps. So the three times no need to analyze circuit from the basics. So this is the advantage. So we find first R Thevenin's by turning off 32 voltage source, that is short circuit, and replacing it with a short circuit, and 2 amps current source, just open circuit, replacing it an open circuit. The circuit becomes what is shown in figure. So how the circuit is becoming here now? See, just remove this one and open circuit this one. Then 12 ohms parallel, nothing will come here. And when you short circuit, 4 ohms will come like this. So 4 and 12 will be the parallel. then plus 1 ohm will be the in series, looking from the A and B terminal. So 4 and 12 is the parallel and 1 is in the series. So 4, 12 parallel is nothing but 3 ohms plus 1 ohm, 4 ohms will come. So the total R Thevenins by simple way if you calculate 4 ohms is coming. Now we need a V Thevenins voltage source, equivalent source. Now just uh, expand this one. We have one loop, then another loop here, then open circuit here. So we need open circuit voltage here, A and B. What is VThevenin's? If we don't have any dependent sources, then just we need a open circuit VThevenin's. If we have dependent sources inside the circuit, then we have to supply a 1 volt, 1 volt voltage from A and B terminal or 1 ampere current from A and B terminal, so that it can be easily understandable, easily analysis. Now, first loop equation, if you write, what is happening? Minus 32 and total resistance of due to the I1 is 16 plus 16 I1. Other current is in 12, that is minus 12 I1, 12 I2, minus 12 I2 equal to 0. Just check. देखिए minus 32 plus 4I plus 12 I1 minus I2 is equal to 0. And what is I2 here in the second loop? I2 is just rotating. So I2 in opposite direction. That is I2 super. What is this super mesh? So I2 is rotating in this one. I2 is equal to minus 2 amperes. So substitute here. We will get I1. Solving the equation in this I2 is substitute here. Minus 2. We will get VThevenin is equal to 12. What is VThevenin now? Now, when you solve these two equations, I2 is known, I1 and I2 is there. So I1 will be 0.5 amperes. It will come if you substitute here. Okay, minus 12 I2, yeah, it will come 0.5 ampere. You can do it that way. So now what is VThevenin? So VThevenin is nothing but the voltage across this 12 ohms resistance or across the voltage across this 12 ohms. What is the voltage across 12 ohms? Because current will not give any voltage. And in this 1 ohm resistance, there is no current is flowing because of the open circuit. So the parallel branch, this parallel branch voltage is nothing but a VThevenin. So VThevenin is equal to resistance multiplied by current. So resistance is 12 multiplied by I1 minus I2 current. 12 I1 minus I2 is the current. So 12.5 minus or minus minus 2, that is minus 2, that is 2.5 into 12, that is 30 volts VThevenin. Another way of calculating VThevenin is these two elements. So what is the voltage across these 2 points is nothing but 32 minus 4 into I1. That is I1 is 2. So for I1 is 0.5. 0.5 into 4, 2. So 32 minus 2 volts, it is nothing but 30 again. So another method also is okay. Now coming to the equivalent circuit. Another method I told you, 32 minus VThevenin by 4 plus 2 also VThevenin. Okay, alternative. Okay, no, I think 96. Yeah, another method also it is doing, no problem. Now, how it look like now? This is a VThevenin's voltage source, and there is a 4 ohms resistance, and the current IL in load resistance connected back. Previously, we removed this load resistance, and in across A and B, from looking back from the right hand side to the left, we found VThevenin's as 30 volts and 4 ohms as a R Thevenin's. Then we connect back this RL. Now find IL for each value of the RL. So IL equation we can write as VThevenin by there is total voltage divided by total resistance. So VThevenin by RThevenin plus RL. So 30 divided by 4 plus RL. 4 plus RL. Now every time RL you can find. What is RL when RL equals 60? 6 plus 4, 10. That is 3 volts, 3 amperes. Now 3 amperes. Now when RL is equal to 16, substitute is 16 here, 16 plus 4, 20. So 30 by 20, 1.5 ampere. When RL is equal to 36, 36 plus 4, 40, 30 divided by 40 is nothing but 0.75 ampere. So like this, we have to calculate the different load currents when load resistance are only changing, only load resistance we are changing. These generally useful in your communication circuits by varying the resistance, how the communication signal will be improved, like that. Okay, now another example with the some voltage source dependent thing. Find the Thevenin's equivalent of the first circuit in terminal A and B. So here across terminal A and B, we are not giving any RL here. Just we are giving a one circuit across A and B. We have to find the Thevenin's equivalent circuit. So in this, what we have 1, 2, 3, 4, 5, 6 elements are there. One is the current source and one is the dependent voltage source. This is the which type of voltage source? A dependent voltage controlled voltage source. See, this is basically a voltage control. Vx is voltage control. What is voltage source? It is voltage type. That is diamond shape plus minus means voltage. So this is a voltage control voltage source. Where it is controlled by in this 4 ohms resistance, it is controlled here Vx, this Vx value. So we have to find the VThevenin. Just check. This circuit contains a dependent source unlike the circuit in the previous example. To find R-Thevenins across A and B, we set the independent sources equal to the zero. So independent sources equal to zero means we have to short circuit this if any voltage source is there. But this is a current source. Then we have to open circuit it. Dependent source no, do not touch becomes the okay that's alone okay because the presence of the dependent sources. However, we excite the network with a voltage source V0 connected to the terminal A and B. Then we may set V naught. We have to connect a voltage source here V naught, which is with 1 volt or anything you can. 1 volt is optimal we are using to ease the calculation, or connect a current source with 1 ampere, up to you. Since the circuit is linear, our goal is to find the current I0 through the terminals and then obtain RThevenin is equal to 1, that is V0 divided by I0. Alternately, we may insert 1 ampere's current source across this A and B and find the corresponding voltage V0 and obtain RThevenin is equal to V0 by I0, that is 1 ampere. So we'll see the step by step. This is only just explanation. Now we have to start. Now I'm connecting a voltage source V0 across this one to find the RThevenins. So what is the value of A and B across means what do you have to do? Just connect the 1 volt source here and apply the loops. So just remove the, as per the rule of the RThevenins, we have to switch off the any independent sources. The 5 ampere is the independent source, so we are open circuiting it because it's a current. If it is a voltage, we can short circuit, but it's a current, we are open circuiting. So across these four, nothing is there. So only these 1, 2, 3, 4, 5 elements are there. 1, 2, 3, 4, 5 elements are there. Across A and B terminals, we connected a voltage source V0, fictitious voltage source, we can say our own voltage source, to calculate the current I0 with a value of 1 volt. Now we have three loop equations. When dependent sources are there, slightly the equations will be more, loops will be more, but process is same, simple. Okay, now first loop equation, because it's a voltage source. What is the first loop equation? It has the two currents. So my current is leaving plus terminal minus 2Vx plus 2I1 minus 2I1 minus 2Vx plus 2 times I1 minus I2 equal to 0, same thing. Then we note that Vx, where is the Vx here? Vx is in the circuit figure, Vx is equal to 2 will cancel and minus time I2 minus I1 minus I2. Vx is equal to I1 minus I2 from this equation. Just solve. 2 will take out this side and 2 will cancel. This minus will cancel out. Then Vx is equal to I1 minus I2. One equation is coming. Now second loop I2. What is I2 here? Current leaving the terminal, that is 4 5 6 6 6 12 12 I2 minus 2 I1 minus 6 I3, all are opposite in direction, so equal to 0. Now let's check. So but minus, okay, again uh, okay, in the previous equation, what is Vx we have to find, but minus 4I2. What is Vx is nothing but minus current leaving. So minus 4I2, minus 4I2 is nothing but Vx, which is equal to I1 minus I2. Now substitute this one, then I1 will become okay, then I1 will become from minus 4I2 is equal to I1 minus I2. So minus I2 take out this side. So I1 will become minus 3I2. So from this equation again solve it. This I1 we got it minus 3I2 in terms of I1 and I2. So we can omit the Vx. Now in the second loop, that is plus 4I2 plus 2 I1 I2 minus I1 plus 6 I2 minus I3. So this is the second equation. Just rearrange that one. So then third loop we have 6 I3 minus I2, 6 I3 minus I2 here, 6 and 2. How much is this one? 2 I3 plus 2 I3. And what is the voltage? Current entering the plus terminal. So plus 1 volt because the V0 is 1. So equal to 0. So we have 1, 2, 3 equation. I1, I2, and I3. Three are knowns and three equations we have. So we can solve for I1 and I2 and I3 directly from your calculator. So I3 you will get it minus 1 by 6 amperes. Then I2, but here there is no I0. Okay. Now what is I0? I0, I3, if you know, then we can find everything. No need of I1 and I2 to calculate. But we have to calculate, but we need I3 actually because I3 is nothing but minus I0. I3 is nothing but minus I0, which is what we got I3 as minus 1 by 6. So I0 is nothing but minus or minus plus 1 by 6. So then what is R Thevenin now? R Thevenin is nothing but V0 divided by I0. So V0 already we know 1 volts what we applied. I0 what we calculated 1 by 6. So 1 by 1 by 6 is 6 ohms. So we got 6 ohms is the R Thevenin. So this is the slight 3 or 4 steps more if when we have a dependent voltage source. If it doesn't have dependent voltage source, then directly just open circuit terminal looking back from the terminals and just equivalent circuit, equivalent resistance we have to find, means series and parallel combination. Okay, now what is VThevenin we have to find. So VThevenin's now we need open circuit voltage VOC across here. If you want VOC and keep back the original current source or any original independent sources, keep it back and just we have to find the open circuit voltage VOC across this. What is open circuit voltage across A and B is nothing but across 6 ohm resistance. Let's see. Okay, to get VThevenin, we find VOC in the circuit. Applying mesh analysis, we get what is the first mesh analysis? Because the super mesh, the current is I1 is in the same direction, so I1 is equal to 5 ampere. In the current in the second loop, we have 4 I1 minus I2 minus I1. Second loop minus 2 Vx. Yeah, second loop, yeah, I'm considering this one here. So this is current leaving leaving this plus terminal. So minus 2 Vx. Yeah, current leaving. So minus 2 Vx plus 2 I3 minus I2. 2 I3 minus I2 equal to 0. So rearrange what is Vx is equal to 2 will cancel I3 minus I2. Vx is nothing but I3 minus I2 from the second equation, this loop. Now this loop, I2 loop, 4 I2 minus I1, 4 I2 minus I1, 2 I2 minus I3, 2 I2 minus I3, plus 6 I2, plus 6 I2 in the same direction equal to 0. Now rearrange, or we rearrange this one, I2. How many I2s are there? I can 4, 5, 6, 6, 6, 12. 12 I2 minus 4 I1 minus 4 I1 minus 6 I2 minus 2 I3 minus 2 I3. Yeah, because I2 is these three resistances together 12. Then other current is 4, other current is his 2. So 2 I3 and 4 I1 is the other currents. So 12 I2 minus 4 I1 minus 2 I3. Rearrange this, it will come same thing here. Now, but 4 I2, 4 I1 minus I2. What is 4 I1 minus I2? 4 I1 because current will give here, right? So current should enter. So we have to take positive. Current should enter means I1 should take. 4 I1 minus I2 is nothing but your Vx. Okay. Now solving the equations here. Solving the equations all the equations, then I2 will become 10 by 3. So Vx, if we substitute here, one equation here, I1 is 5, and I1, I2, and I3 again here. Now substitute all the three unknowns, three equations, because here Vx is more unknown, fourth unknown, 1, 2, 3 equations, four unknowns were there. But we know what is Vx, 4 I1, 4 times I1 minus I2. Substitute here, then three unknowns and three equations. So directly we can get. But what we need only I2. Here in 6 ohms resistance, we need I2 only. No need of I1, I3 to be remembered. Just I2 we need. So I2 is equal to 10 by 3. We got it from these equations. Now, what is VThevenin is nothing but 6 times I2 current entering. So, VThevenin is nothing but 6 times I2. So 6 into I2. What is I2 here? 10 by 3. So 3 to the and 20. 2 into 10, 20. 20 volts is VThevenin. Then we got VThevenin as 20 volts. RThevenin we got, I think, 6 ohms. Right. So this is your equivalent, the Thevenin's resistance and Thevenin's voltage source of the original circuit. What it has one current source, it has dependent voltage control voltage source, and some 1, 2, 3, 4 resistances. So this is your equivalent circuit. Okay. So like this, we have to calculate the Thevenins. Now go to the Nortons. Nortons is same principle as Thevenins, but here we need the short circuit current. We need the current here. In Thevenins, we find the voltage, open circuit voltage. Now here we need the Thevenins. Thevenin's voltage, open circuit voltage in Thevenin's theorem. In Norton's, we have to find the short circuit current. Norton's theorem states that a linear two-terminal circuit can be replaced, same like Thevenin's theorem. A two-terminal linear circuit can be replaced by an equivalent circuit, one equivalent circuit consisting of a current source IN a current source in parallel with resistance RN. So here current source will come and in parallel with a resistor RN. But in Thevenin's, a voltage source V Thevenin's and in series RN, like your source transformation, we have a current source IN that is called Norton's current, and in parallel a resistor RN, this is called Norton's resistance, where IN is the short circuit current through the terminal. So the terminal where we open circuited the load resistance and that the terminals we have to short circuit one wire. Then we have to find what is IN, and the Rn in the is the input or equivalent resistance at the terminals when the independent sources are turned off. So Rn is same like a R Thevenin's. We have to look back into those terminals and open circuit the current sources if any, and or short circuit voltage sources if any, and find the equivalent resistance if all our independent sources are there. So same rule for dependent also, that will come in later. So this is your definition. So Norton's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of current source IN in parallel with a resistor RN, where IN is the short circuit current through the terminal RN through the terminals, and RN is the input or equivalent resistance at the terminals when the independent sources are turned off. Okay, the Thevenin's and Norton's resistance are equal. So how we are calculating Rn? Yeah, Rn is nothing but is an input or equal resistance at the terminals when the independent sources are turned off. Same definition is coming for R Thevenin's also. So that's why Thevenin's and Norton's resistance are equal. So this is a linear circuit A and B. Just open circuits at A and B and switch off all the independent sources and find from looking back from these terminals the equivalent resistance. So there is nothing about R Thevenin's. Here also R Norton's. Same thing it is. To find Norton's current, now what is our Norton? Because IN we need. To find the Norton current, we determine the short circuit current flowing from the terminal A to B in both the circuits. So across these A and B, we have short circuit, and we have to find what is the current will flow. Okay, so that is IN. So check the other circuit. So here also, what is IN is nothing but the current what is flowing across A and B when it was short circuited with the original circuit. That is nothing but for IN. Okay. Okay, if it is obvious that the short circuit current is IN, this must be the same short circuit current from terminals A and B. So if you see here the current, what the current A and B is flowing is nothing but if you remove RN, the same current will flow here. So that's one. So the current IN is nothing but ISC. When short circuit, we call it ISC, but the same, it is nothing but as per definition, it is a Norton's current. Dependent and independent sources are treated the same way as the Thevenin's theorem. So dependent sources, how we have to treat? We cannot open circuit or short circuit the dependent sources. And for finding the R Thevenins or R Nortons, we have to apply what we have to apply. We have to apply a voltage source of 1 volt or a current source of 1 ampere. Then analyze the circuit by KVL or KCL and mesh analysis, node analysis. Then find out the what is the current there when you apply the voltage source. Then voltage by current is nothing but R Nortons or R Thevenins. So, or if you apply a Norton's current, sorry, you apply a 1 ampere current, then find the voltage, find the IN in the same way. Then what is the voltage we are getting? So, voltage divided by the IN 1 ampere is nothing but your R Thevenins or R Norton. Same way, in the same law what we did in the Thevenins. We will do the example. The Thevenin and Norton equivalent circuits are related by a source transformation. That's why we studied source transformation in second topic, or third topic. Yeah, third topic in this chapter. Then we started the Norton's and Thevenin's theorem. So that's why what is source transformation? Source transformation is nothing but a voltage source in series a resistor can be replaced by a current source with a resistance in parallel. This is source transformation for any linear circuit. Homogeneous linear circuit. Okay. The close relationship between Norton's and Thevenin's theorem is nothing but Rn is equal to R Thevenin, because the procedure of calculating the equivalent resistance in Norton's and Thevenin's is both are same by looking back into the open terminals of A and B and just switching off the independent sources, right? So that's why both are same, Rn and R Thevenin's. Now we know that IN is nothing but V Thevenin's by R Thevenin's. So IN we can know that if we already calculated V Thevenin's, then V Thevenin's by R Thevenin's, the equivalent circuit is nothing but IN. Then R Thevenin's is also known as RN. So we can replace by source transformation. Let's have one example. Okay, okay, some more items. Since IN and VThevenin R are related according to the 4.11 equation, IN is equal to VThevenin by R Thevenin. To determine Thevenin or Norton equivalent circuit requires that we find open circuit voltage across terminal A and B. So we have to find A and B like what we know VThevenin's. The short circuit current across terminal A and B, IN. Then we can find what is RThevenin. So RThevenin is nothing but VThevenin by IN. It's easy. The equivalent are input resistance at terminal A and B when all independent sources are off. Then we can find the RThevenins or R Nortons. We can calculate any two of the three things because IN, VThevenin, RThevenin. RThevenin is equal to RN. So we can calculate any three of these. Three using the method that takes the least effort and use them to get the third using Ohm's law. This is the Ohm's law. IN is equal to VThevenin by RThevenin. VThevenin is equal to VOC. So we know that what is open circuit voltage is nothing but VThevenin. IN is nothing but short circuit current. If we short circuit, then RThevenin we know VOC by ISC, which is equal to RN. Also VThevenin by IN Norton's is also RN or RThevenin. Both are same. So any three if you find, fourth one is easy. The open circuit and short circuit tests are sufficient to find any Thevenin or Norton equivalent of the circuit which contains at least one independent source. If we have dependent sources, then we have some one more step we have to follow. But if we have independent sources, then open circuit or short circuit tests are sufficient to find Thevenin or Norton equivalent. Let's have an example here. Okay, find the Norton equivalent circuit of the figure at the terminal A, B. At the terminal A and B, find the Norton equivalent circuit. What is the Norton equivalent circuit? We have to find. So we need IN and we need RN. So first we can find with the RN, that is because we doesn't have any dependent sources. Just we have to independent sources. We have to switch off. How to switch off? Just open circuit the current source, short circuit the voltage source. So short circuit here, open circuit here. Then 8 ohms by looking back from terminal A and B, 8 ohms, 4 ohms, and 8 ohms will be in series. So 8, 8, 16 for 20. 20 ohms will be equivalent of these three in series when we short circuit voltage source and open circuit current source. Then 20 ohms and 5 ohms will be in parallel, and that will be the resultant R Nortons. So 20 into 5 divided by 25, 4 ohms. So 4 ohms will be your Norton's resistance. So see, open circuit this 2 amperes and short circuit here these two. then the circuit will be like this. 8, 4, and 8 will be in series. So 8, 4, and 8 in series. 5 ohm, 5 ohms will be in parallel. Then 4, this is 20 and 5 in parallel. 20 into 5 by 25. Then it will be 4 ohms is your equivalent resistance Rn, which is equal to R Thevenin's. Now, how to find ISC? So, short circuit, original circuit is this one, short circuit this A and B, and find IN. So, short circuit this A and B, and keep back these voltage and current sources. We have one loop here, two loop, three loops. We have three loops, but two loops is enough. Okay. So, first loop, I1 is nothing but 2 amperes. Now, second loop, we have to find. Let's see. So when it is short circuit is here, the 5 ohms resistance effectiveness will go because it is short circuit. Because zero resistance is this one. This is your 5 ohms resistance. Then what? When there is a resistance is zero, the complete current flowing in 8 ohms will not divide into 5 ohms because it will go completely in the other branch. That is a 0 ohms resistance. So 5 ohms will be become nullified. So two loops will be there, I1 and I2. So first loop I1 already we know that is 2 amperes in the same direction. Then we have to write the equation for this loop, that is minus 12, which is it? Yeah, minus 12 uh, plus 4 I2 minus I1 plus 8 I2. This is the third equation. Just solve that one. So I1 is nothing but 2 amperes. Now second equation minus 12 I2 minus 12, sorry, okay, minus 12 here, minus 12 here. I1 is flowing opposite to this I2. So 4 minus 4 I1 minus 4 I1. Now I2 is flowing in 1, 2, and 3, 1, 2, and this 3, 8 ohms, 3 resistances. 5 ohms is gone. So 8, 8, 16 plus 4, 20. So 20 I2. So 20 I2 plus that is plus 20 I2 minus 4 I1, which is opposite direction, and minus 12 is the voltage source equal to 0. So I1 already know, substitute I1 here, 2 amperes, 4 to the 8, 8 plus 12, 20. Then I2 is nothing but your 1 ampere if you take it. I2 is nothing but 1 ampere, which is also known as short circuit current. What is I2 is nothing but same as short circuit current IN, and which is also known as IN. So IN is 1 ampere, or N is 4 ohms, then the equivalent circuit will be. Another way we can find open circuit also. Alternately, we may obtain IN from the VThevenin by RThevenin. We know the RThevenin is equal to RN, so we already got 4 ohms. Okay, open circuit. Okay, now I3 is from this open circuit, same circuit what we have here, same circuit, open circuit voltage. If you find, we can find the IN also. So in this open circuit, we have if you find the voltage across 5 ohms, then there is nothing but your VThevenin's. Okay, now Ethereum is nothing but open circuit voltage VOC. We have two loops now. Now 5 ohms will be in the circuit. It will not be zero because it's an open circuit here. So first loop equation I3 is equal to same direction 2 amperes. Now loop equation of I4 is nothing but total resistance is how much? 8, 8, 16 for 20, 25 ohms plus 25 I4, that is 25 times I4 minus 4 I3 because it's the opposite direction of I4. So minus 4 I3 current leaving. So minus 12 equal to 0. Okay, I3 is 2 ampere. Now see 25 means total resistance in I4 is 25 minus 4 I3 minus 12 equal to 0. So I3 already known. Substitute here 4 to the 8. 20, 25, it is 0.8 because it is 20 divided by 25. It is 0.8 amperes is nothing but your I4. Now, what is VOC? VOC is nothing but I4 times R. That is I4 times 5 ohms. So I4 times 5 ohms. That is 5 I4. I4 is 0.8. 5 into 0.8, 4 volts. So VOC is nothing but VThevenin's. What is VOC? Nothing but VThevenin's, which is equal to 4 volts. 5 into 0.8, 4 volts. IN is equal to VThevenin's by RThevenin's. That is, we know that IN is equal to, as per the source transformation technique, IN is nothing but V Thevenin by R Thevenin. That is 4 ohms, 4 volts. We got 4 ohms. What we got in the previous slide, 4 by 4, 1 ampere. So previous slide also we got IN by short circuiting also we got 1 ampere. Now also we calculate by V Thevenin, and if you divide with R Thevenin, we got 1 ampere. So this is how equivalent circuit can be formed. We have two methods I shown here. We can use any one of the method to make less steps. Okay. So this is your 1 ampere with RN is a 4 ohms and IN is a 1 ampere. So that is your 4 ohms. Now let's go to the another one. We have here last example in the Norton's. So we have to find what is the Norton's current here. Let's see. We have dependent sources. Using Norton's theorem, find Rn and In of the circuit A and B. Of the circuit A and B, we have to find In. So what is the In? Now check here. This is a dependent current, current control dependent current source. Current control current source it is. Okay, 2Ix and current source in the direction of right side. Okay, now let's see. This is a circuit. Then we have to short circuit here, and we have to find the Rn. Okay, just short circuit here. We find the Rn. If you know the ISC, then we can know the IN. Now let's find. First, apply voltage source V0, 1 volt across these A and B terminals. Then we can find the what is the VThevenin, sorry, R Thevenins or R Nortons. So we are applying here the 1 volt, so 1 volt source here. So then open circuit this voltage source because we have to remove that one in finding the resistance, equivalent resistance, maybe RN or maybe R Thevenins. Just remove this one. This voltage will be as it is. Our current source will be as it is, which is a dependent. Then what happens? It will look like this. So 10 ohms. So when we short circuit this one, we cannot remove this 4 ohms resistance because of the short circuiting this 10 volt source because it is depending, the current is depending on this element, dependent current source. So that's why we cannot do that one. So what we do, let's see. To find the RN, we set the independent voltage source equal to 0. This independent voltage source equal to 0, that is short circuit and connect a voltage source of V0 across terminal A and B. Across terminal A and B, we are connecting a 1 volts or any unspecified voltage V0. Anything we can give 1 volt, 2 volt, up to you. 1 volt is optimal. We obtain the circuit as shown in figure here. So we'll get the circuit like this. We ignore the 4 ohm resistance. Okay, now we can ignore the 4 ohm resistance. Later we can find what is Ix one resistor because it is short circuited. So because here short circuited, we can ignore for the momentum. Later we have to again apply. Also due to the short circuit, here due to the short circuit, the 5 ohm resistance, this 5 ohm resistance because this is the current. 5 ohm resistor, the voltage source 2Ix because 2Ix because of the short circuit. What is the 2Ix? The voltage source and the dependent current source are in parallel. The voltage source and dependent current, these two will be in parallel. Okay, because this is short circuited, this is removed, and this point will come to up to here. Okay, so this point will come to at point B. So these two will become in parallel. So what is the current I0 will divide in these two terms. So now and dependent source are in parallel. Hence, Ix is equal to 0 because this Ix is equal to 0 at node this one at node Ix is equal to 0 because of this short circuit. At node A, I0 is nothing but 1 volt divided by 5 ohms. Because already we know because of this short circuit, Ix becoming 0. Nothing is flowing here, removing. So this will not come into picture. So only 5 ohms will be there. I0 is nothing but V divided by R. That is 1 volt divided by 5 ohms. So that is 0.2 amperes. We got I0. Now what is Rn? V0, what we gave 1 volts, and what is I0 is nothing but divided by is nothing but your Rn. V0 divided by I0. 1 by zero point 0.2 is nothing 5 ohms. So we got 5 ohms is the Rn. Now we need ISC, which is equal to IN by short circuiting this one. Keep back the voltage source what we removed. Then find the loops. To find IN, we short circuit the terminals A and B. We short circuit the terminals A and B. So then, as indicated, note that this figure 4 ohms resistor, the 4 ohms resistor will be in picture. 4 ohm resistor, the 10 voltage source, and 5 ohm resistor and dependent current source are in parallel. So the 4 ohms and When it is short circuited, what's happening? Just check here. 4 ohms, and because it is short circuited, it is going down. It is going down. So 4 10 voltage circuit and 5 ohms and 2 ix all are in parallel. Because it is going in parallel. So just rotate this one like this. So it will go like this, means 5 10 4 and 2 ix. Both are, all are in parallel. So ix is nothing but 10, because the same voltage will be there all the branches. So ix is nothing but 4 divided by, 10 divided by 4, 2.5 amperes. We got ix. Then hence that node A, what is node A? How many currents are there in node A? Current is leaving is nothing but ISC. Current entering is nothing but 2ix, and current entering is nothing but 5. So ISC is nothing but, what is ISC is nothing but, one current is this all are in, okay, 10 divided by, V1 minus V2 divided by, uh, uh, that is what is current here entering from this 5 ohms is nothing but V1. What is V1? 10 volts, because higher potential, minus at this one 10 divided by 5, because in parallel in 5 ohms, in parallel both are same. So 10 volts divided by 5 is the current in the 5 ohms, that is 10 divided by 5 plus 2ix current entering here, at node A, plus 2ix. So 10 divided by 5 is 2 amperes. 2x is nothing but 2ix. Ix already we know 2.5, 2 into 2.5. So total is 7 ampere. At node A, current is nothing but 7 ampere, which is also known as IN. So the equivalent circuit is like this. So now next class we'll study about the maximum power transfer, inshallah.
Now, coming the maximum power transfer. So last topic in this chapter, maximum power transfer means at what point the circuit behaves like it is getting a maximum power in the complete scenario. In many practical solutions, a circuit is designed to provide a power to the load. The load resistance between terminal A and B on the right hand side is a load resistance generally. So in that resistance, we have to deliver maximum power. So how it can possible? There are applications in areas such as communications where it is desirable to maximize the power delivered to a load. Means in communication networks, we always think about the power should be delivered maximum during its working. So how to find that one? The Thevenin's equivalent is useful in finding maximum power a linear circuit can deliver to a load. So we have two options, Thevenin's and Norton's. So Thevenin's always is useful to finding the maximum power. If you have Norton's also no problem, but you have to, so by using source transformation, you have to convert to Thevenin's, then you can find the maximum power. Easy, because in the Thevenin's, the voltage source will be in series with a Thevenin's resistance and the load also in series. So all are in one loop only. In Norton's, there will be two loops, source current and the Thevenin's or Norton's resistance and the load resistance. So the calculation will be quite bigger than the Thevenin's. So let's go with the Thevenin's one. We assume that we can adjust the load resistance. No, every time now change the load resistance so that we can see when the power is maximized. If the entire circuit is replaced by its Thevenin circuit equivalent, except for the load as shown in figure, the power delivered to the load will be. So now we just, this is the load resistance where we want to vary every time, so that we have to find at what point the power is transferred maximum. So now on the left side between terminal A and B, we equalize with the Thevenin's voltage and Thevenin's resistance. Now vary the RL. Now as per this loop, what the equation we can write for the power? I square R in this current. What is the power in the resistor RL? Is nothing but I square into RL. This is the power delivered to this resistance power equation. Or VI also you can put, and V is nothing but your VI also you can use VI into R you can put. So I square R will come. I power 2 and RL. Now what is I? So what is I in this? It's nothing but voltage division rule we can use. What is I? Voltage division rule. It is total voltage multiplied by the same resistance, where we want to find the I, divided by the total resistance. So total voltage divided by the total resistance multiplied by RL. That is your complete this one. So I is nothing but V Thevenin's. What is the current? V Thevenin's divided by R Thevenin's plus RL. Right? V Thevenin's divided by R Thevenin's is the current, because it's one loop only. This is one loop. All these two resistances are in series. So V Thevenin's by R Thevenin's plus RL is nothing but your I. So it is power 2 multiplied by RL. That is resistance in where we want power. So that resistance we apply I square R, then it is your power. Now when it will be the maximum power? So just increase the RL every time, then which is equal to R Thevenin's. Then it become 2 times RL. So 2 times R Thevenin's. Let us take RL when become R Thevenin's, it become 2 times R Thevenin's. Here also R Thevenin's. One V Thevenin's power 2 divided by 4 times R Thevenin's power 2. So 1 R Thevenin's will cancel. It become V Thevenin's power 2 divided by 4 times R Thevenin's. We'll see that one. So maximum power is transferred to the load when the load resistance equal to the Thevenin's resistance as seen from the load RL and R Thevenin. From seeing this time, I am varying the RL, so that when it will be maximum, when these two resistances are equal, then only the current will be the maximum. When current is maximum, power is maximum. So when these two are equal, then only maximum power is transferred. So now see, we will see the graph also how it is there. For a given circuit, V Thevenin's R Thevenin's are fixed. We cannot change because the circuit is fixed one. By varying the load resistance, the power delivered to the load varies as shown in the sketch. 4.49. See here, this sketch, you can see the variation. This is the RL on the x-axis and the y-axis is the power, how it is transferred. Now, change the resistance RL, because RL will increasing here every time. Then the power will increase, right? P square, then when RL is here and here, both are there. When RL I am increasing, here power is there. So it will increase up to the point maximum RL is equal to R Thevenin's. Then it will decrease again. If you want, you can have some 5 or 6 step values of RL, we can find which is equal to R Thevenin's and which is less than RL and which is greater than R Thevenin's. Less than R Thevenin's, 1 point you can use, and greater than R Thevenin's you can use another point. See the power calculation. It will be equal maximum at R Thevenin's is equal to RL. Okay, you can find out, no problem. In example also you can show it. So at the point where RL is R Thevenin's equal, then at the point only the power is maximum. This graph is very, very important. Maximum power transfer graph. You can, if you ask to draw, you can have to draw this one. Now we notice that the power is small for small or large values of RL, but maximum for some values of RL between 0 and infinity. Between 0 and infinity will be very small, but here it is maximum. Now let us see. We now want to show that this maximum power occurs when RL is equal to R Thevenin's. This is known as the maximum power theorem. When R Thevenin's is equal to RL, or RL is equal to R Thevenin's, then only the power is maximum. So this is also called as maximum power transfer theorem. Now next, we have an example. Find the value of RL for the maximum power transfer in the circuit of shown in figure. Find the maximum power. So this is a circuit between terminal A and B. There is a RL, and this is your main circuit where we have to find V Thevenin's and R Thevenin's. Then we have to find the maximum power. So directly maximum power we can't find without knowing the V Thevenin's and R Thevenin's. Okay, so just remove the RL and find the V Thevenin's and R Thevenin's first. Then keep the RL and find the maximum power. Okay, now R Thevenin's. How to find the R Thevenin's? Remove the RL. See from this side, from the left to right, we have to just solve the this circuit. And for solving the circuit, you have to make power of the sources. Power of the sources means 12 volt source. Voltage source is short circuit. Current source is open circuit. So this short circuit is here. Then 6 ohms and 12 ohms will be in series. Now in open circuit, this 2 amperes, it will become open here. So these 3 ohms and 2 ohms will become in series. So the 6 ohms and 12 ohms will be in parallel. Then whatever the result is coming, these 3 will be in series. So 2 plus 3 will be in series. Then 6 ohms and 12 ohms in parallel. That is nothing but 6 ohms into 12 ohms divided by 18 and 4. This become 4. So 4 plus the 3 plus 2. 6, 7, 8, 9 ohms. So this is 9 ohms is the Rn. In one step you got the R Thevenins or R Nortons. Anything is same. So next we have to find the what is the V Thevenins. So across the terminals remove the RL and open circuit this RL and find what is the voltage across this A and B terminal. So across the A and B terminal we have to find the V Thevenins, and these 2 ohms will not come into picture because it is an open circuit here, because we are open circuiting here, and these 2 ohms will not come into picture because current will flow in the closed path only. So now we got 2 loops here, the same circuit. We got the 2 loops, one is I1 and I2. So find the 2 equations, 2 unknowns, then you will get the answer for the V Thevenins. Now what is I2? I2 directly we can have with this. I2 is equal to minus 2 amperes because it is flowing opposite direction. I2 is minus 2 amperes. Now find the first loop equation and substitute this I2 minus 2 amperes in that, and you will get the I1. Once you get the I1, what is here, this is open circuit, this current is not come into picture, and the voltage here is nothing but your V Thevenins. Now we'll check. So minus 12 because current leaving, plus 6 and 12 18 I1 minus 12 I2 because I2 also current is there. Now we know from the second loop I2 is nothing but minus I2. Now substitute, we will get I1. So I1 is nothing but, if you substitute in this, minus 2 by 3 is the I1 from these 2 equations. Now apply KVL around the outer loop to get the V Thevenins across terminal A and B. So it will be minus 12 plus 6I plus 3I2 here outer loop. So this one, because 3I2 2 into 0, there is no resistance here, 2 into 0 plus V Thevenins. So then you can find V Thevenins as the 22 volts outer loop. To find the V Thevenins, it's not for the mesh analysis, it is for the finding the V Thevenins. So V Thevenins is now 22. Now we got for maximum power, RL must be equal to R Thevenins. So what is R Thevenins? We got it here 9 ohms. So RL will be same 9 ohms. So power equation is P is equal to V square by I square R, and that is nothing but V square by 4 RL if you substitute. So it is 22 is the voltage power 2 and 4 is the multiplication and 9 is the RL, that is R Thevenins. So 13.44 watt is the maximum power that can be delivered to the circuit, not more not less. It is that point where RL is equal to R Thevenins. This is the power, peak power we will call. So this is how we will find the maximum power. So we have some problems also, practice problems, where I use 2 problems for superposition, these 2, and 2 for source transformation. Answers also given. Now another 2 questions for the Thevenins, these 2, and 2 questions, 1 question for the Nortons and 1 question for the maximum power. So we can find it. Okay, thank you for chapter 4 is finished now. In chapter 5 we will study about the another passive elements, inductance and capacitance. We will see that one. Okay.